Right, so as I was saying, welcome back to day 4, the last day, so please be awake for one more morning. We have Badr today talking about the theory of variational inference, which is all you have been waiting for, a bit of theory, so please.
Thank you. So thank you everyone for being here, for the invitation. So today I'm gonna end this masterclass series with the talk on the theory of variational inference. So, sorry, yeah. Sorry?
Click on the slide once, the mouse.
Get him out. Yeah, I'm sorry.
Now the clicker will work.
Yeah, okay, thank you. Okay, sorry. Okay, great. So just before starting this talk, I just would like to highlight a thing, which is like what actually Leo Breiman called the two cultures. So Leo Breiman is the inventor of the random forest. So actually, it's like two point of views of statistics and machine learning. So you have like mainly the statistical, the modeling point of view on statistics, and the predictive one. So basically, in classical and standard statistical inference, you observe a collection of data, which are random variables, and which are which have some. So in the AIT framework, some common data generating process P star, which is unknown. So we are given data, we are given a model, and we want to, so which is assumed to contain the true distribution P star, and we want to recover the distribution are from the model and the data. And in the predictive point of view, so it's a bit different in the sense that in the standard supervised statistical learning, we observe a collection of variables which are pairs. So basically inputs and outputs, for instance, classification, regression, and so on, which are ID from an unknown distribution P star. But what we want to do is not to recover the true distribution, but to recover the relationship between the outputs. So we are given a set of predictors or a hypothesis H, and we want to find the best relationships, the predictor, sorry, that will be able to predict the output while given a new input. So this is, I mean, the difference between the two tasks is not very clear, and I mean, some people are interested in the first one, the second one, in both. But when you're talking about statistical inference, basically in general, you're tackling the first task, even though it's more complicated than that, and you can do really other things such as uncertainty quantification and hypothesis testing, a lot of things. But basically, when you're doing statistics, you're more or less doing this, and machine learning more or less. So I know that this is really caricatural, but I would like to insist on that because the framework we'll adopt in this talk is the first one. So we're in Bayesian statistical inference. So we will consider Bayesian and variational inference here because this is the topic of the masterclass, of course. But I insist on the fact that actually to prove results using this framework, we use so mainly pack-based theory, which is incorporated in this framework. So what we will try to do today is to provide a theoretical analysis of variational inference, okay, using so the first setting. So we will try to answer a few questions. Actually, the main properties of standard classical Bayesian inference have been studied in the past decades. So the question we'll try to answer today is, how about, what about variational inference? So do variational approximation retain the same properties as exact Bayesian posteriors? Which are the conditions under which such approximations are consistent? So what consistent means here? And all these conditions different. And so the outline of the talk, first we'll present some results in pack-based theory, because this is the main theory that we will use. So using the predictive approach, then I will present the main results in variational inference and consistency of variational inference, and finally 2 small examples with mixture models and sparse deep neural networks. So of course, feel free to interrupt me at any point if you have any question. And also we will have like 2 short practicals during the talk, so mainly prove like a pack-based inequality and to derive a rate of convergence for mixture models, right? So a few references. So first, if you're interested in pack-based, so there are like two recent reviews on the topic. So I refer you to these two reviews if you're interested. So regarding the consistency of variational inference, so mainly the talk will be based on these three papers. So these three papers have all been submitted the same year, so in 2017, all been published the same year, 2020, and in the same journal, the Annals Stats. So more or less, what they're doing is exactly the same thing. They are analyzing like what is called the concentration of the posterior distribution. So there are other works on the consistency, which is quite an unclear, undefined notion of consistency of convergence. So there is mainly the work of that Jeremiah that studied like a generalized variational inference using a notion of consistency, which is a bit different, which is basically the concentration of the posterior of the approximation of the posterior on Dirac measure. So you stop me if I'm saying something wrong. And the work of Yixin Wang and Dave Bly, which do more or less the same thing with the study of some Bertrand Familly's theorems. But this is beyond the scope of this talk. So I will mainly focus on these three works. And so two applications, so two papers I have written, so on mixture models and on sparse deep neural networks. So first, a study of pack-based. So the framework in statistical learning, in supervised statistical learning, is very standard. So basically, you are given a training data set, which is, so in a supervised setting, you have like inputs X and outputs Y, okay, which was IID from some unknown distribution P star. So two small examples, so binary classification, just imagine that you want to classify images of cats and dogs. So this is very standard. Or you can have not a binary output, but a space, but just a regression task where what you want to predict is a number, a real number, right? So this is very standard. To predict the output given the input, you consider some functions. So you're given a class of hypotheses or predictors, which are functions from the input space or to the output space, Y, which can be, as previously, a finite space in the case of classification, a continuous space in the case of regression. And the way you evaluate the quality of your prediction is using some notion of some loss function, right? So assume that Y prime is either a cat or a dog, and Y, the true answer, is either a cat or a dog. You're evaluating the quality of your prediction by here saying whether or not it is a mistake. If it is a mistake, you suffer a loss of 1, or if you're right, you do not suffer any loss, right? So to evaluate the quality of your predictor H, what you're doing is that you're considering a sample of a pair input-output following the data generating process, and you're evaluating the quality of your prediction. So is your prediction close to the true answer, so either a label or a number using the loss function, and so you consider this expectation. So this is a standard notion of a risk. So this is what we can call either a theoretical risk or a population risk. So this is very standard, nothing new for you, I think. So what is the prediction rule? So the only difference with the rule prediction, I just mentioned here, which is a function from the input space to the output space, is that here, so the entries of the function is composed of a data set and a feature, right? So here, this complicated space is just the space of the data set. Right here, this is a pair input-output. To the n, this is a data set of size n, and this, I just say that, okay, you can consider a data set of any size. So this is very standard. So what I'm saying is that a prediction rule takes as an input a data set, a feature, and outputs what he thinks to be a good prediction for the feature which is given as an entry, right? And in general, you will be given the data set, okay? So the only thing is that you are given a data set, so you learn a prediction rule, right? And then you're given a new input, a new feature here, and you try to predict the right output. So in the following of the talk, I will just omit here dependence on the data set, and we just put an end to mention that this prediction rule is data dependent, okay? So here, this is a random quantity, which randomness data set, Okay,
And okay, the only randomness is from the data set.
exactly. This is just to say that the hat with the n means that the randomness, this is a random quantity that comes from the data set, and the data set is of size n, of course.
That means, for example, the training procedure is purely deterministic, for example.
Yeah, for the moment, yeah. But yeah, for the moment, I mean,
So like classical SVM, let's say.
sorry?
Like classical SVM, like you're doing convex optimization, there's no,
For instance, yeah.
no stochasticity anywhere.
But there's no SGD or anything like that.
Now, yeah, that's what I said, like classical SVM.
Yeah, after, I mean, regarding the GD, I mean, you can like, you will be able to incorporate some other source of randomness, but it will be precise at some point or not.
But like, you know, statistical learning theory expects convex objectives, and so you can use that.
Okay. So this is just to really set up the notation, okay? So the risk of a prediction rule, so I just have to, to adjust a bit the definition, because it's just to say that here the expectation, the randomness is in the expectation just comes from the draw of the pair XY. And here, this definition of a data set, okay? So here in the expectation, you have two sources of randomness, one from the data set, the other one from the draw of the pair you want to predict. Here you only consider randomness according to the pair XY, and here the data set is considered as fixed. So it's conditional. And actually, what is learning about? Learning is about the ability to generalize. So it is the prediction, the ability, sorry, to predict beyond the already seen data set, right? So basically, what you're doing is that, of course, when you learn, I don't know if you're a student, you're learning a lecture, you're preparing for an exam. Basically, you want to, of course, you want to learn what you've seen in class, but what you want to do in the end is to be able to be good the day of the exam on new questions, basically. So it is in a way the ability to generalize. So how is it possible to quantify this ability to generalize? So this is a question we'll come now. So the ability to predict well on unseen data is exactly what we just defined. So this is the population risk of the prediction rule, right? And the ability to predict well on already seen data is what we call the empirical risk. So how well we are good on the data sets, on the training data set, right? How would you quantify your ability to generalize? It is by a quantity that is called the generalization gap. So this is something that is very simple. The generalization gap is this quantity in blue here. It is the difference between the population risk and the empirical risk. So if this quantity is large, it means that your population risk is much higher than the empirical risk. So you're much better on predicting things that you have already seen than on predicting new things. And if this quantity, this generalization gap is small, this means that you generalize pretty well. So this generalization gap is blue, is typically the quantities that can quantify your ability to generalize.
Is it clear that it's positive?
Sorry?
Is it clear that it's positive, the difference?
Not necessarily, but in general and in expectation with high probability, this is a positive quantity. Because if it is negative, it means that you're better at predicting new things than predicting things that you've already seen. This is something that, I mean, if you consider a standard algorithm, this will not be the case. In general, this is positive, but it is not, I mean, it may be some cases where it is a non-positive quantity. And what we want to do in statistical, I mean, some subfield of statistical learning theory aims at controlling this generalization, right? And this kind of inequality is called, so Jeremiah spoke it yesterday. It is called like a pack bound, which means probably approximately correct. So probably means with high probability, and approximately correct means that it is correct approximately. So the generalization gap is small. So here, the probability that with high probability holds over the training data set, because the random quantity comes from the training data set here. Okay, the only randomness here is hidden in the data set. So with high probability, the generalization gap is small. So it is the kind of things we want to achieve. Is it possible to be sure, or to be almost sure, to be sure with high probability that the generalization gap of our learning procedure will be small. So if you have this kind of inequality, what that means is that the learning algorithm that you're considering, the procedure H and hat, is something that generalizes well, right, over the training data set. So typically, this quantity which controls the generalization gap can be written this way. So it quantifies some measure of complexity. It depends, of course, on the level of confidence and on the training data set. The more data you have, the smaller this quantity will be, right? And what is pack-based about? Pack-based is exactly about this kind of inequality, but not for a single hypothesis, but for distribution of a hypothesis, right? So I will precise it later, but this is everything this is about. So we will consider pack generalization bounds, but over distributions, for distributions, right? So what kind of pack bounds exist?
Excuse me.
Yeah.
By complexity, do you mean capacity of H?
So what do you mean by capacity?
Like, let's say how many parameters are you are using of our A parameter?
Yeah, exactly. So, well, this is a good point. Actually, when you mean capacity of H, what is H in your case?
I mean, in your case, like H is the predictor, right? So I
Okay.
can have the predictor with one parameter, I can have with 100 parameter, and that. So I was just wondering that by complexity, do you?
Yeah, exactly. Exactly. The point is that, so this is an interesting point because the complexity may depend either on the precise predictor you're considering, in which case, in this case, this is really dependent on the predictor you're considering, or this can be the capacity, if you mean capacity of the whole hypothesis class, which can be uniform. So yeah, this is exactly the kind of inequalities that exist in practice. And the particular point is that in pack-based, this complexity depends on the precise predictor you're considering, right?
This is the fundamental program of machine learning, right? So,
You know,
but just like in those contexts, the word capacity is used all the time. So like we have empirical risk minimization.
exactly. This is a.
So I was just wondering that, but
Thank you. So basically,
Sorry, one question.
Yeah.
In the top line, what is SN? What is the conditioning on, please?
SN, you mean here? This is a training data set. So what I mean is that given a data set, the population risk of the prediction that I am considering is equal to this. And given that, I am given the data set. So this quantity is conditional on the data set that I'm given.
Okay, thanks.
Welcome.
Just to clarify, so this is just the generalization gap, right? It could be the case that both of these risks are really high, right? So it doesn't actually say it's good. It's just good at generalizing as opposed.
If you're considering a prediction rule that is making predictions uniformly at random, this is equal to 0.
Right.
So this is basically a trade-off between memorizing, so setting this small, and having this difference, which is the capacity to generalize, small as well.
Right, I see.
So this is a trade-off. That is why I was saying that I was a bit caricatural here, because it's not only the capacity to generalize, but it's much harder to find the patterns behind generalization than behind memorization. So to come back, so this is a relevant point, because here I wrote the generalization gap on the left. Here I split the generalization gap in two. So you have clearly what is your target in the end, because your target is not only the capacity to generalize, but the size, the value of your population risk. And here you have like your capacity to memorize. So basically, what generalization bounds are about is that they give a guarantee on the performance enhancing data that they control by the capacity to memorize the data plus a control on the generalization gap. So this is basically you memorize, you generalize, okay? And why is it interesting? Because like they give a guarantee, of course, but what is interesting is that they can be computed with the training data set only. What does that mean? It means that sometimes in machine learning, you use your training data set to learn your learning algorithm, and then you use another data set to evaluate your learning procedure, which is not the case here. So you use the training data set to learn the procedure, right? The algorithm, and then you use the same training data set to have warranty, which is pretty nice, actually. You only need one data set, so no need to split any data set or something like that. The second thing is that it provides a computable control on the test error. What does that mean? It means that if I give you a learning algorithm and I'm telling you what is the value, the population risk of my algorithm, you will not be able to answer the question because you do not know what is the data generating process. And of course, if you do not know the data generating process, this quantity is unknown as well because it explicitly depends on the data generating process. So basically, you cannot say, okay, my population risk, let's say my classification risk is equal to 10%, but I can tell you that it is no more than something that I can compute. And for instance, it is possible that this is equal to 10% and this is equal to 2%. And then you say, okay, I don't know that it is equal to 10%, but I can tell you that with high probability, it is no more than 12%, for instance. Okay, this is something that is nice as well. And it's a lot of researchers are interested in that point in particular. So computed tight generalization bounds on complex architectures. So a third one is that it may explain why learning algorithms work. For instance, by going back to the notion of capacity, of complexity of your generalization bound. And finally, it leads to designing new algorithms. Why so? Because in the end, what you want is to hide this quantity in blue to be small. Okay, you want this quantity in blue to be small. You cannot minimize this because you do not know. You do not know in practice what the population risk is equal to. But instead of saying, okay, it would be good to have like a predictor with a small value of this, you can say, okay, ideally, I would just like to choose a predictor H such that the bound is small. If you know that this bound is small, then this quantity in blue will be small as well. So basically, a new learning procedure would be, okay, I will choose my algorithm by minimizing the right-hand side. And this will be kind of a trade-off between memorizing and generalizing, right? So this makes it possible to design new learning algorithm. Choose a distribution H, a predictor H that minimizes the right-hand side, okay? So what kind of generalization bounds do exist in practice? So maybe the most simple one is this one, which is a standard concentration inequality. So basically here, this is a random quantity, okay, which is centered around this one. So this is very easy to prove the first one. This is a basic concentration inequality. So if I am given one predictor, H, I can prove very easily that this is true, okay? Now, the fact is that here, you see that the predictor H is deterministic. Why so? Because I said, given a single hypothesis with high probability, I can say this. So basically, here I cannot consider any data dependence in the distribution H. A way to consider the data dependence would be to swap the order of with high probability and for any hypothesis. Why so? Because if you say with high probability over the training data set, I have for all hypotheses, then the hypothesis is allowed to depend on the training data set, which would not be the case if you swap this order, okay? Because the training data set does not even exist when you consider the single hypothesis. And it is possible to swap actually the order of these two sentences by doing one small thing, which is like, I think that most of you may be familiar with that, a union bound argument, right? So you can swap the both. So if you consider a finite hypothesis class, you can say that with high probability, you have for any predictor this, and the only thing that you suffer is a logarithmic dependence of the size of the hypothesis. Okay, so this is true, and this is quite convenient to work with this kind of inequality because now you know that this is available, valid. This bound is valid for any H. So in particular, whatever the H that you choose, the inequality is still valid. So for instance, in particular, you know that the population risk of the empirical risk minimizer is no more than the empirical risk of the empirical risk minimizer plus the small quantity. So now that you have this inequality in this order, you can choose the predictor that you want, even if it depends on the data, right? If the hypothesis class is not finite, you can do many other things. So using like notion of Rademacher complexity, the Fatnik-Cherfenenkis dimension, and so on. This is not the main focus on the talk, so I will not spend too much time on that. But the only thing I would like to say about this is that pack-based it's exactly the same thing, but it just allows us to consider distributions of a hypothesis. So instead of considering a single hypothesis, even if it is data dependent, I want to consider distributions of it. Okay? Are there questions for the moment? Great.
It's the distribution, I guess we're going to see, but are you saying when we say distribution of a hypothesis, that's more than just a distribution that's induced by the data in some sense? Or is it like, yeah, like what does it mean to consider a distribution over A?
Just to say that actually what I will do is that I will consider expectations over the rate. So the kind of quantity I will consider exactly this one. So I want to know if I consider a sample of H according to Q in expectation, is it possible to control this quantity?
Where H is no longer like a function of the data, it's sampled from Q essentially.
I mean, Q will be the tool, the mathematical tool that will depend on the data.
Right.
So I want to learn a randomized or stochastic predictor in a sense. This distribution will depend on the data. So Q will be able to depend on the data. And I want to say, in expectation, if I sample from my randomized procedure, is it possible to control this risk in expectation? This is what I mean. So typically, so in pack-based, so I work with a prior distribution, but I want to insist on the fact that this prior doesn't mean anything. So in Bayesian inference, in standard Bayesian inference, prior distribution has some precise meaning. It represents your prior beliefs, something that is precise, it's unique. In pack-based, it doesn't mean anything. It's just a distribution. It's quite convenient to work with this because in general, it has the same place as the standard Bayesian inference, but just like Jerome has presented it yesterday, so it's very flexible. The framework is very flexible and it's not precisely the same prior distribution as in standard pack-based. The same way, the posterior doesn't mean anything. So it's not the standard posterior distribution, it's just like a distribution, but distribution which will be of interest, okay? And so we'll consider this, I mean, it's not proper distance, but discrepancies between distributions by using the KL divergence. So I just recall the definition, but I bet you are all familiar with that. And as I just told, actually the risk that I will consider, so I will not consider a single hypothesis, but distributions of a hypothesis. And the risk of these distributions will be exactly defined like that. So I sample one hypothesis according to my distribution Q, and I look at the population and the empirical risks of my sample hypothesis in expectation. And in pack-based, the question I am trying to answer is, what is the behavior of this generalization gap? So not the generalization gap of a single predictor H, but what is the generalization gap of a distribution Q? And actually, there exist many versions of pack-based inequalities, okay? There exist many pack-based inequalities. So I just want to present one to you, one of them. Yeah.
Interrupt. So here the data are random or fixed.
Which quantity, sorry?
So the two risk that you have there. One depends on the data, right?
So R is the population risk.
Yeah.
Or N hat is the empirical risk. So it depends on the data.
So there is a conditional expectation there.
Yeah. You can define it the same way. Actually, this is conditional on the data. Okay. So the yeah, you're right. So if let's say here we need, so if Q is data dependent, so you have a conditional, this is conditional on the data. Okay. You're right. You're right to mention that. And not the basic, but there exist many pack-based inequalities. So I give you one because this is the one that we'll be interested in today. So it's written this way in this paper, so Alquier and Chopin, which has been published in 2017. And so you have to know that the main hypothesis, that can be relaxed in some contexts, but the main hypothesis, the main assumption in pack-based is in general, the boundedness of the loss function. So in general, we assume that the loss function is bounded by 1 typically. And we have with high probability for any distributions that are defined over the hypothesis class, this, that's all. Okay. So the notion of complexity here is this one. And so I understand that it can be a bit complicated to handle, but just to give you some, maybe some feedback, some intuition behind that, I just would like to give you another formulation of this inequality. So basically, once again, I'm just reminding you that this is the generalization gap. So what we are saying is that with high probability, uniformly of a Q, the generalization gap is no more than this, plus this, plus this. So this comes from the confidence level. So I will just give you an expectation version of this inequality. So instead of saying with high probability we have this, I will tell you in expectation. So the bound in expectation is the following. So here we have the generalization gap. So the expectation of the training data set of the generalization gap is upper bounded by this KL in expectation plus this quantity. Okay. And this quantity is no more here present here because it depends on the confidence level, which does not exist anymore. So this is exactly the same inequality as the previous one. Just instead of giving it in with high probability, I gave it in expectation. So here I explicitly wrote the dependence on the training data set of the distribution Q. Just here it is hidden because saying that with high probability this is uniform of a Q. So Q here is allowed to depend on the data. Okay. If I had not written the dependence on the training data set here explicitly, it would have been hidden. So I prefer writing it explicitly. So what can I do now? You can see that the lambda here is a parameter that I can basically tune. So assume that I tune this parameter. What do I have? I have this inequality. Okay. So the expected generalization gap is upper bounded by this. So how can I interpret this? I'm going a bit further. Here, the prior distribution, I told you it has no precise meaning, but the only dependence this inequality has on the prior distribution is here. So basically, imagine that I choose the prior distribution that minimizes the right-hand side, okay? The prior distribution that minimizes the right-hand side is this one, is the expectation of the random procedure, right? What do I get if I choose this one? I get this. So here, this is the mutual information that is shared between the training data set and the learning procedure. What does that mean? This typically quantifies, so this is a notion of capacity, actually. This quantifies. The question is, what can I learn? What does the learning procedure reveals about the training data set it has been trained on? And this mutual information, which is an information theoretic quantity, exactly quantifies that. So if this quantity is large, it means that the learning procedure, so if you take a look at this procedure, so just imagine something that is deterministic. So you have a neural net, and here this is a neural net with some learned weights. So having this quantity large, this means that when you take a look at the weights that you have learned, you have a lot of information on the training data set, the weights have been learned, right? So what does that mean? It means that there is an information, a mutually shared information between the learning procedure and the training data set that is very large. So this means that there is a kind of a lack of stability. There is a strong dependence on your learning procedure on your training data set. So you can expect one thing, which would be this generalization gap to be large. I don't know if I'm clear. What I mean is that if I am taking a look at the learning procedure, and just by taking a look at the training procedure, I can tell you a lot of things about the training data set without even knowing the training data set. This means that your learning procedure is strongly dependent on the choice of the data set, and is very less likely to predict, to generalize well, okay? Because when you have the ability to generalize, you do not want to have a strong dependence on the training data set, on the particular data set you train your learning procedure on, okay? So typically, you can see this scale distribution, this distance between the posterior and the prior as a notion of information that is shared between the training data set and your learning procedure. Okay, so of course, I tune a lot of things and so on, I agree. But in the end, it was just to say that this scale is very connected to a kind of information theoretic notions that is able to give you some, that quantifies some notion of generalization, okay? If by just taking a look at the learning procedure, I know a lot of things about the training data set, then, which means that this is large, then it is very likely that I generalize this poorly, so this is large as well. Yeah, Jeremiah?
So,
Go ahead.
yeah, but like in neural networks, we know about the phenomena called double descent, right?
Yeah.
So in case like in those cases, there is no indication that the weights are not related to data set, but yet we see the generalization, the bound, I mean, like at least the empirical loss still going down and down, where theoretically it should be.
Well, this is a good question. So it's hard to just really explain the double descent just using this framework. It's true. But basically, the fact is that this is some quantity that does not depend on the number of parameters. So you can have a very, very large notion of parameters and this quantity being small. So this is, so the capacity that you're looking at is not typically the number of parameters, but some notions of information that is shared. And in neural net, if you evaluate this in practice, this is still small. So in practice, this is not in contradiction with the yeah. So it's not possible to explain precisely the double descent. It's true,
but like the classical, like at least like the classical risk minimization framework, not the back bus, but like how you explain capacity, that contradicts what we see in practice.
Yeah, but
You know
typically that fits.
That's why I was asking, right? Because you're
So
framing it in a different.
So yeah, it works actually pack-based to the best of my knowledge on the only bounds that are tight in other parameterized settings. So this is why it is quite popular actually. So this is far from being really not interesting, but I mean, how to say, like to explain everything and to be even. So there is still a gap, I think, between things in theory and in practice in pack-based. This is not, the pack-based bounds are not really used in practice. But if you evaluate your pack-based bounds in really upper parameterized settings, these are giving very, very relevant results.
They were used to be used back like 10 years back. John Taylor used to use them.
Yeah. I mean. Yeah, Jeremiah.
So just to check my intuitions here, right? So Q hat S for me is usually the base posterior or the variation of posterior, right? If we can just minimize the bound on the previous line, then we get that. Then it's interesting to me, I haven't really had much exposure to the information here, theoretic generalization bounds. But if I read it correctly, basically what it means is you want in expectation the discrepancy between your posterior and your expected posterior to be small, right? So in some sense, the variation in the posterior with the random data you sample is small. So the frequentist perspective on the posterior is basically, well, if you look at the KL as a notion of variance in the measure valued estimator, which is not quite what it is, but it gives you like a measure of how much that fluctuates. You want that fluctuation to be small.
Yeah, exactly.
So if your Q hat S was a point estimate in the space of measures, that thing would be 0, right? And then you again get like a really good generalization bound, even though it's practically meaningless.
No, it is exactly the opposite. I mean, if this is a 0.1 centimeter, this is equal to this explodes actually.
Oh,
This is equal to infinity. So basically, it's why, I mean, some people take a precise look at the behavior of these inequalities, and precisely this is why it is the limits of this kind of inequalities, which is that if you consider like pointwise estimators, for instance, just single neural nets, I mean, so the mutual information is exactly the expectation of the KL between this and this, okay? So this is the definition of the mutual information. And actually, if you consider like pointwise estimators, so Dirac, this is equal to infinity. And people to be able to evaluate some bounds in the case of pointwise, I mean, deterministic procedures, in the sense that it's not a distribution, but a single hypothesis that is learned. So with possible randomness coming from SGG or something like that, actually, they still use this kind of inequalities, but with, I mean, it's not cheating, but with incorporating some like variations with, with ghost procedures and the incorporate some kind of variance to evaluate that precisely and so on, to get rid of this exploding distance. But there exists as well some other information measures of information theory, mutual information using other distances, for instance, the Wasserstein and all these kind of things which may not explode. And that's a lot of things that exist, but
It's fundamentally a mismatch of support problem.
yeah. But this is really a good remark because so I did not mention it, but explicitly, if you consider the Iraq here, it explodes. So
Thanks.
Saf had a question as well, I think, from on.
yeah, sure.
Saf, do you want to just unmute and ask? You there? Saf, do you want to just? Oh, you can't. Okay, well, he's typed a question, which is how do you interpret the Fisher information?
The Fisher information.
Maybe he was just referring to the mutual information.
Yeah, here is the mutual information. So the mutual information is exactly what I try to explain, at least, is that it really quantifies what the learning procedures reveals about the data set it has been trained on. It's exactly this. So typically, if this is a small quantity, it means that by looking at your learning procedure, at your predictor, you cannot say a lot of things about your training data set, which in a sense means that you generalize well, and as a consequence, this is small. So in a sense, this is, sensitive, right? So to come back to the inequality, now I will just, so maybe like a 15-minute practical session, I will just ask you to, if you want to prove this one. So I will give you some hints. So to prove this inequality, you can use three ingredients. So the first one is really fundamental in fact-based. This is a change of measure inequality in the sense that it provides a control in expectation with respect to Q as a function of an expectation with respect to pi plus the KL. So of course the KLs here come from there. Okay. Another inequality that I think most of you are familiar with, which is Markov's inequality. So I directly gave it with the form that you need to use. And the final one is Hövding's lemma. So of course, just a spoiler, here you can see that the KL is this KL. So you need to choose a right choice of F. And here the Hövding's lemma is here to control an exponential moment. So this exponential moment that you so here the x f h when h follows pi. And so yeah, I'll let you try to prove this. Maybe 15 minutes.
Yeah, okay. As a generalized.
Yes, more or less an indicator function, get from expectation to probability. And the second thing to the third thing.
Okay, anyways, it's bounded. So you were F in the possible.
Sorry? Yeah, exactly. Trying to figure this out.
Okay. This must be a typo, surely in the.
No, I don't think so. KL diverges between Q and
Q. Yeah, that's fair.
I don't know. The slides. I don't know.
Start from the left hand side. Then you have to perspective difference. You apply the first one and then obtain the expectation of difference. Third.
That we did.
No.
At all.
Yeah. Yeah, it's almost this one. Just like you just need as well to, to multiply by lambda. Just like the function f is just like the generalization gap, but weighted by lambda, so that you
Just need to add the lambda at the end to make it match that.
Yeah.
Which is why I have a lot more brackets than I should
The,
have.
the lambda is quite important here to consider the lambda inside the on top of the.
Yeah, no, I just defined activity and I took the lambda out. Because I added it at the end.
What is this? Sorry.
This is lambda.
Yes, but the lambda has to be considered here. Just
in front of one
yeah,
of them.
Yeah, just in front of that. So f is lambda times is this, yeah. But the lambda will be here.
Yeah, fair enough, because then you don't divide
Yeah.
that by that.
So basically, by considering lambda times the generalization gap, your actually consider generalization gap to a lambda factor. Then you will have the log of the expectation pi of the exponential
of the difference of
and
that.
this exponential of nanana is a random quantity basically.
That you control with the third one.
You control with the third one, but first you apply Markov's inequality to control the expectation of the exponential with respect to pi by an exponential with respect to pi and with respect to the data set. So in the end, what you want to have in the first quantity in the right hand side is a log of a double expectation.
Okay.
And to get this double expectation, so the x in the Markovs will be exponential of f of h with the x being here the data set. I mean the randomness being for the data set.
Yeah.
Oh, I think I see what you mean.
So you have exactly this.
Yes.
Here, yeah. So here, this exponential will be the x in Markov's inequality. And then you control this, which will be the log of this, the double, this will be a double expectation because of the Markov. And then you control what you have. And this is exactly all you do. Everything you do. Nothing more. Yeah. Yeah. Yeah, the thing on the top is what you include in the three gradients.
These steps.
So
Yeah, you just need to multiply this by lambda. So basically the function f will be lambda times the general value. I mean, I'm saying this because the lambda is in the exponential. Yeah. So basically,
So this is okay.
yes, this is okay. Then to
And then
control,
I'm stuck because I'm not
Yeah.
using really.
of course, so here, what you want to Markovs is if basically the organize Markovs will training data set. So this exponential will be controlled by the expectation with respect to data sets. So this, okay. Then you will get here the double expectation with respect to part and with respect to the data set.
So I have to take an expectation with respect to x. Both sides.
I mean, the x here, no, I mean, just like now, this is part of the second step. And just put it on the second. We will have this. By its expectation. So here, control of this, control of this, but we don't need the probability, sorry. By expectation with respect to the training data set. So I have to stick to the. Yeah, exactly. So this is. Yeah, exactly. But then, so the here the x. And the ability of the train data set. There is no x here.
On the
Yeah. Exactly what you need to do.
but then I have to say we
Yeah, exactly.
break on that.
Exactly. This is exactly. High probability is this by that.
And then expected
Are we also assuming that the loss is bounded?
Yeah, I'm sorry. You assume that the loss is bounded by one.
Oh, by one,
It
okay.
will be used in halving.
Yeah, exactly. I'm thinking what B and A are, so.
Yeah, A is 0 and B is 1.
Okay, yeah, thanks.
bound with probability
Yeah,
better than that.
And now you use bound. Oh, so this is the double. This. For this, by adjective input. So here, the random quantity
Of the expectation.
I mean, this is centered because the random quantities are hot. Yeah, I mean, the sign doesn't really matter
The
because.
expectation of
Yeah, exactly. The expectation with respect to S. I mean, you don't expectation. You just with respect to S. Yeah, I mean, this one doesn't matter.
yeah, okay.
This is this two. You might respect to this. What is it? But you can because I'm sorry, just to say it's yeah, I mean, I think you still brought H because you have to consider the expectation with respect to H. So
Okay.
just consider a single expectation. Then
Finding.
Having you just have to use the fact that the loss is bounded by one, so the loss is positive. Bounded by one. So here A is.
The loss was minus half.
No, so this is the generalization. The empirical loss is just R hat. So here R hat is. Yeah.
So.
Yes, allowable data that's don't Because I mean, you just consider the expectation with respect to F. So this is what you bound in the embedding, but you still need to consider expectation with respect.
Oh, yes.
I mean, it's up to you. How you do that.
There's like one technical phase, which
Yes.
is like a transport inequality thing, but everything else is really expensive.
It's a good excuse to.
Yeah. What is zero?
Thank you. I'm just gonna.
A is zero.
Oh. Oh, yeah, the bounce on the. We're talking about.
Yes, so here, the random variable, which is bounded by one each. Due to the fact that, it's like an average of.
That was so much. We lost there. Oh, it was so right. The mood immediately like. Yeah, no, it's great. Okay. No. Actually, I was supposed to be fashion something.
So now you can see that there is no longer any dependence in H because this is.
What are you
doesn't
meaning?
depend on H, right? So this is good. Okay. Then you split the log one. Log of exponentials, we just not
Well, it's kind of related to something, yeah.
Cool. This one, cool. Yeah, it's pretty simple actually. The inequalities are pretty simple.
Yeah.
I mean,
Yeah, I'm not better than the board games, yeah.
the fact is that all foundation inequalities not always have the same forms. So the only difference is
Slightly darker than you.
Where does the n come from?
N.
Which is the n lambda, right? N.
Yeah, sorry, yeah.
Well, sure that, yeah.
Actually, the fact that
You haven't been here before.
No, I like that one.
maybe I can write like
Yeah, everything else, I just don't know where this.
Yeah, I'm sorry, I just forgot this one. The fact is that here, so the this is between 0 and 1, right?
Wow.
Yeah, that's good.
The empirical loss, typically it's like great, okay?
Yeah. So they are very different.
Yeah, but still, even if it is between 0 and 1, it's highly concentrated, right?
Yeah.
So you can use this fact by saying that, okay,
Are you seeking like?
so what we want to control expectation of the exponential of lambda times s h minus o
Right, like-
h, right?
Yeah.
It's
And you can write it like that, so basically.
Oh, so this is kind of the general version of the Heffing inequality, right?
Yeah, exactly, it's
Yeah,
Heffing's,
okay.
but you just like this as lambda times, so it's 1 over n. Let's write that like xi, okay?
Oh, because it's a sum, and
Yeah. So
yeah.
it's 1 over lambda over n times the sum of xy minus
Because they don't know.
expectation of x. This is central,
Yeah.
okay? Just to write this, actually, this is like product, so this is the sum, so this is a product. You can use the independence to swap it, just like exponential of lambda over n times xy minus x.
You describe.
No, but.
So now xy is between 0 and 1. So
Yeah,
it's having, which is like the product
to someone.
of the exponential is bounded by lambda squared over n squared times minus 1, which is 1.
Yeah.
And then, given that it is a product, you multiply it by.
Yeah.
So you get times squared over n squared.
Yes.
So you use the fact that it is independent
Right.
swap the expectation and the product to get the squared over n.
This is cool.
Yeah.
Thank you.
Welcome. Enjoy this practice. I'm sorry, you haven't. You,
It's not like.
Oh, no, I'm gonna go to the bottom. I haven't, done it yet.
Yeah.
I used the first ingredient, and then I kind of got stuck.
okay, so the first ingredient, basically, the fact we'll use is this one, so the generalization gap.
Yeah, exactly.
Okay,
You can see because of the formulas and things like that.
exactly. So now you have this inequality quite easily, so you have the KL, Q and pi.
Yeah.
Okay, now what you need to control is this. So you have the expectation with respect to pi of the lambda times the generalization gap, right?
Yep.
So to control this, actually, you control this by the double expectation, okay? S of this. By 2s, I just get divided by delta. Yeah, actually,
No, I don't want any
here, the randomness that you use in Markov's is the randomness that comes from, because here is a random quantity in the data set
as well, yeah.
Yeah, I'm paying.
So you use Markov's inequality, but with the randomness coming from this. Okay? So this is a delta. So the first part was shown probability 1. Now to have this is upper bounded by the log of
So what
I'm old enough to say.
Yes.
plus the KL between Q and pi.
Ah, okay.
And the last part is we will, because now you have the log here. So you already have this part, right?
Mm.
This part comes from
Yeah.
this,
Yeah.
and then the remaining quantity is this one, okay? And what you will do is that you will control this
Actually, no, so it's Sunday.
using Havding's lemma.
And then you get the log and then, okay, I see.
And Havding's lemma, you control this one by using this.
I don't know.
So I wrote an equality, but no.
Maybe it's a joke.
Also, you write this as an expectation of, so you just, so yeah, if you write this xy, you have, use the fact that this is a sum, an average.
Yeah.
Then you use the product dependent,
Are you gonna close one?
then you have this, and you use the,
You know, if you come to this phase, you
to run
want.
it. We use something with 0 and 1, so this is equal to 1.
I mean, I think that can be clear what is happening.
Which is then,
Or otherwise, that one's empty probably.
so this is
Not sure.
the remaining quantity.
They were quite expensive.
Log of
Busy on the weekend.
Like, it's just reckless.
Then you divide everything by lambda.
Yeah, of course. I've heard a similar talk before because the Alkier,
Yeah,
he gave a talk about probability.
okay, great.
There's a PhD student who's working out for 2 years.
Actually, I was his PhD student, so.
Ah, you are?
Yeah.
Do you know Tatiana?
Yeah,
Yeah.
I know him.
Yeah, he was in Oslo for many years.
Oh, you are in Oslo?
Yeah.
Okay, great, yeah.
And,
He left.
he's in further north in Norway. Trondheim,
Really?
doing spatial stuff there.
Okay, I didn't know he's even in Orange North.
Yeah.
Okay. Okay, I didn't know.
Yeah, like also he also presented some of the pack-based stuff for us. It was a small group of. We were not many Bayesians there in that group, just maybe 5 people.
Okay.
And we never really got anything. Never really got anything.
So basically,
He's doing cool stuff.
Yeah, that's, yeah.
just an expression. I think that's good. I just. That being,
Tell us about the prior you choose for that date. The paper.
and then
It's a prior that's essentially integrating over the sample space.
the third. But even.
All my intuition is like formal Bayesian training tells me that that's wrong. Like it's breaking the stack principle, all this kind of weird stuff.
Here.
But it's interesting as well because it's and the mutual information.
So basically,
There's the line of thought in like objectification inference.
I mean, these things are given.
So prior distribution
This is whatever. target
maximizes the missing information between the prior and the prior.
Then
Is
there.
that connected to this somehow in some way?
Yeah, in a way, I think it's like a loop.
Okay,
It's a bit like surprising because
like this one.
when you do PyBase, you're doing like the terminology of Bayesian inference, but you're not doing proper Bayesian inference.
So
And if you want to like
This one.
or closer, I mean,
The minus.
varieties or this kind of one of this, it is quite possible just to
Just added.
optimize the
Send me.
Yeah, exactly.
and I think it's interesting in this kind of work.
Doesn't mean that the others don't.
I said previously, it's not that I had to optimize with respect to lambda, I had to optimize with respect to pi. And
I love it.
Zero.
I think in the sense that you can just like
Guys,
find some kind of Bayesian terminology, but people with other communities and try to find interesting interpretation.
minus the creed. It's also possible there's a
I did my master thesis.
the Mala example.
And obviously,
They always try to they maximize the entropy or they maximize information theory quantity regarding the information constant in prior there. And you choose your prior that's furthest away
Yeah, okay.
while still allowing proper procedure.
you did everything.
It's important.
Yeah, exactly. That's quite
Yeah,
but I haven't seen this here, so it takes a while to get into this.
Yeah.
That's big.
That came 2 years ago. Sorry, yeah, to my director. He came 2 years ago, right?
That's yours, yeah.
Is
For COVID.
X, yeah, is V. So then
Oh, yeah, I was early in my PhD. Yeah.
is Y.
Important.
Okay. Yeah.
Oh, cool. Nice to meet you.
This
I
guy.
will,
Continue, yeah.
This one, other notes was but minus. That's the.
show you.
Oh, okay, you're unsure on that. No, really. Well,
I think that it actually.
we are sure.
Right.
Yeah, but we don't intend to.
So now
we use the theorem.
also per partes argument that you need to. Integration per parts argument because the.
We're actually trying to.
I don't know if I missed some pluses and minuses in this expression, that's not possible.
She's invited.
Are you sure that?
I've missed the veil so far.
I took. But last, it is okay, but the wrong. I don't know.
She doesn't believe.
I decided that we'll
Good.
start again. Just for them all.
The plus minus.
And up.
Disagree.
Okay,
It's also should be verified if it's disagreement.
We're not doing, my life was,
all right, you were gonna reach you guys?
Yeah, I agree. But I mean, the technique of how I'm gonna.
Okay, guys, so we're going to dive into the proof. So basically, what we will do here, you can see that the kernel here is used only in the Donsker variance lemma, so this change of measure inequality. So basically, what you understand is that basically F would be related more or less to this generalization gap. So exactly, F will be equal to times the generalization gap, so that you can recover the final inequality from this one, okay? So you consider this choice of F, so I write this like with a hat and an N to highlight data dependence of F, okay? So basically, I choose F to be lambda times this generalization gap. So what do I get if I combine the first inequality and the second one, okay? So basically, I exactly get this. Why do I get this? Because here, F is a data dependent quantity. So either I can just write it like that with F here being a random quantity, F here being the exponential being a random quantity, or I can upper bound this exponential by its expectation using Markov's inequality. So it's exactly what I did here. Here, the exponential of fn hat, I upper bound that by its expectation with respect to S using Markov. So if I did not use Markov here, I would just get this, okay, which is a fully stochastic quantity, and I would get this, sorry. And if I use Markov, I get this with high probability, okay? So the first ingredient with this choice of F, I mean, even without this choice of F, but if I consider a random quantity here without Markov, I get this without any probability, I mean, with probability 1. And if I incorporate markup, I get this, okay? So given that pi here is data free, I can swap the two expectations and I get this. So basically, if I apply this inequality, which is a combination of the first ingredient and the second one, I get exactly this. And if I apply this to this particular choice of f, I get this, okay? With this function m here, being an exponential moment, or at least a logarithm of an exponential moment being here, okay? So what I see is that I'm almost done, because here, what I wanted to show was that this was upper bounded by the KL divided by lambda, so I get it, plus the log of 1 over lambda divided by, 1 over delta, sorry, divided by lambda, so I get it here, because I split the logarithm in two, and there is only one remaining quantity, the lambda over 8n here, which is not present here anymore, but instead we have the logarithm of this exponential moment, okay? So the only thing left we have to do is to control this exponential moment, okay? So if I write this using, yes, like splitting the logarithm in two, I get this. So I just want to control this exponential moment m of lambda n, for this one, so that this m divided by lambda is equal to lambda over 8n, okay? So this is exactly the same thing. Just a reminder of what I wrote here, okay? So I'm here now, and I just want to control this by this divided by lambda over 8n. And the fundamental ingredients I use here is Abdine's inequality. So I wrote the proof here. So I don't know if everyone can see. No? Okay. So basically, I'll try to...
The other pen might be better.
Sorry?
Another pen as well.
Okay, I mean, right. So basically, the red maybe, no? The orange one. So basically, if I... Do people see well or not? Yeah.
With the black.
Maybe the black, yes. Do people see well? Better? Okay, great. So basically, that's regarding the, maybe I can do this, I don't know.
Okay, no, you can stay, you can stay. Yeah, that's fine, yeah.
Okay.
Playing with this thing, I'm just gonna zoom in a bit more.
Okay, great. So basically, thank you. So basically, I start from this, I will just get rid of the log, okay? I control that later. I just fix the h, okay? Just get rid of the dependence in h. I consider the expectation with respect to s of lambda times the generalization gap, okay? H is fixed here, we don't care about h. I get this. I write the definition of R of n, right? So it's 1 divided by n times the sum of L, Y, I, H of xi minus R of h, right? So I'm just writing it that xi to go quicker, okay? So I just write this like that. So it's the exponential of lambda times 1 over lambda n, the sum of xi's, minus, so this is the R of h is just the expectation of x. So here, okay, you get like, this is a central quantity because the population risk is exactly the expectation of the empirical one. So I get this equal to 1, okay? To the expectation, sorry. Now, what I'm doing is that I'm just dividing lambda by n. Okay, I'm just considering here a sum. So it's the sum here of xi minus expectation of x. Okay, is everyone okay now? So for the moment, okay, we are fine. So now, what can I say about the exponential of a sum? This is exactly equal to the product of the exponentials. And given that my data are dependent, the expectation of a product is equal to a product of expectations. So this is due to the independence assumption. This is exactly equal to the product of all the expectations, right? So expectation of lambda over n times xi minus expectation of n. Okay? So this is due to the independence assumption. Independence. And the thing is, what can I say about xi here? So here we can even just write the expectation with respect to xi. What can I say about xi here? And I know that xi belongs to 0, 1 by assumption, because xi here is just my loss. And I know that by assumption, the loss is between 0 and 1, right? So basically, I can apply Harding's lemma to xi, which is between 0 and 1. What does that give? It gives me, so I keep the expectation and the product. Sorry, I keep the product, not the expectation. This is bounded by lambda squared, lambda over n squared, okay, times 1 minus 0 squared divided by 8, right? This is just a straightforward application of Harding's lemma. Okay, Harding. Okay. And then this does not depend on I anymore, so I just multiply by n. So it's just exponential of lambda squared to a times n squared to the power of n, which is equal to exponential of lambda squared to 8n. Okay. These are just straightforward computations. So it's what I wrote here in 1 second, one slide, but basically it's quite easy to show that m here is upper bounded. Yes, of course, the exponential moment without the expectation over h is upper bounded by this. So if we add the expectation over h and we add the logarithm, we just get this. Okay. This is something that is quite straightforward to show. And then finally, what do we have? With probability larger than 1 minus zeta, we get our result. Okay? This is quite straightforward. Great. Is everyone okay regarding the proof? Okay, so I go on. So just, it's my last slide regarding the first section. So basically, it's just to say that the general formulation of pack base is the following. So in general, I know that with high probability, the empirical risk, the population risk will be upper bounded by the empirical risk plus some quantity. So here that was this, okay? But it almost always have the same form. It may depend on the choice of the change of measure inequality, may depend on the choice of the concentration inequalities that you choose, but the ingredients are almost always the same. So this is exactly the kind of things that you have. And in pack base in general, as the inequality is true uniformly over Q, you have like some kind of a principal strategy that just consists in minimizing the right-hand side. So a pack-based objective is just to say, okay, I minimize the right-hand side of the inequality. So it's exactly what Jeremiah said yesterday. This is very generalized framework that can lead you to designing new objectives. And then you can solve this using stochastic gradient descent algorithms, Monte Carlo, and so on. Just to say that there are many celebrated algorithms that can be interpreted as pack-based minimizer. In particular, the Gibbs posterior, which is quite popular in machine learning, is exactly the minimizer of this bound, exactly this one. So you can see that so here and here, there is no dependence on Q. So minimizing the right-hand side is just minimizing this. So actually, you can see it is quite easy to prove actually that the Gibbs posterior, is exactly the minimizer of the previous pack-based bound. And even further, if you, to go back to your computational complexity. So if you take into account the computational complexity of minimizing this kind of things, you can just decide to restrict the set of distributions over which you minimize. For instance, say, okay, I don't want to minimize over the whole set of distributions, but just over Gaussian. If you do so, this will exactly be variational inference. So it's just to say that variational inference can be seen as, you know, there is so what you call like the projection point of view and the optimization point of view. Actually, it's true that in variational inference using the KL can be seen as the projection minimizer or as an optimization minimizer, but it's in particular variational inference in particular is exactly the minimizer of some pack-based bound. So I'm telling you this because in the second section of the talk, I will just obtain consistency results by showing that the variational approximation minimizes a pack-based posterior, okay, a pack-based bound. So that's all. So now let's go switch to the consistency of variational inference. So a different framework. So this is the one that we'll use until the end. So the first one has been introduced mainly to show you some results. So we assume that we observe a collection of independent variables. So I'm sorry, it's a P star here. So we assume that we consider a model that contains the true distribution. So P star is here equal to P theta star. So for convenience, we assume that there is a dominating distribution with some common density, but this is not a fundamental assumption. It's just for like simplicity here. We adopt a Bayesian approach. So here, pi is a Bayesian posterior, so it's fixed and once for all, okay? It's not as in pack-based. We adopt a Bayesian approach, so we define the likelihood, given the model and the data. We define the posterior distribution, and just, actually, to be honest, we will not study the posterior, the exact posterior today, but a slight variant of this one that you use to call the weighted posterior, I think, yesterday.
They call it all sorts of things. Power posterior, I think is quite common.
Power posterior.
Seems fractional posterior.
Yeah, fractional. So I will use tempered, but basically this is more or less the same thing. So the only difference is that in Bayes' rule, you just raised the likelihood to an alpha power. Alpha lower than 1 and smaller than 1, larger than 0. Okay, so why do we do that? So there are many reasons for sampling reasons, from robustness to model misspecification, because, so yeah, the question of robustness is a bit tricky, and actually it can be shown that in practice, tempering a bit the posterior may lead to more robust results. So I will not focus too much on this point today, and the final one is that the theoretical analysis is easier. So it's not only the proofs that are easier, but also the conditions that are needed to get the concentration of the posterior distribution. So today I'm focusing on this tempered posterior for the simple reason that the question we will try to answer is not under which condition is the posterior consistent, but under which conditions the variational approximation of the posterior is consistent. And the fact is that the conditions under which the posterior and the tempered posterior are consistent are not the same. But if you want to go from the consistency of the posterior to the consistency of its approximation, or if you want to go from the consistency of the tempered posterior to the consistency of its approximation, you need to add the same kind of inequalities. So I will not study the consistency of this, but the consistency of this, because this is less involved than the proof of this. But in the end, what is interesting is not showing is this one consistent or is this one consistent, but is its approximation consistent, is its approximation consistent. So going from this to this and going from this to this is exactly the same thing, okay? So of course, it would be cool to study this, but studying this is more complicated than studying this, but studying this to its approximation, this to its approximation is exactly the same thing. So I will focus on this one because it's much simpler, and I think I will briefly talk about the case of the exact posterior, but in the end. So, okay, so the computation of, so that will be a review of everything that has been said the previous day. So basically, if you do not have it in explicit forms, you can use Monte Carlo algorithm, basic. When it's complicated, in the last few years, you can have like some more sophisticated Monte Carlo algorithms, some ABC algorithms, so variational inference. We will focus on variational inference. So for the notation, I remind that pi is the prior, pi n is the posterior, pi n alpha is the tempered posterior. I did not put a hat here but it still depends on the data. I did not put the hat because I will use the tilde for the approximation, and I don't want you to get disturbed by this. So basically, without the hat, it's still the posterior, it still depends on the data, okay? So now, the idea of VI is very simple. So the projection point of view, you have a temporal posterior here, which is tractable. You want to approximate it using, for instance, a Gaussian. What do? You project your posterior over the variational set. You can choose parametric distributions. For instance, I can project over Gaussians. I can project over a mean field variational set, which imposes some kind of independence between the parameters. And you have two alternative point of view, either the projection point of view, so it minimizes the distance to the KL, of the KL to the temporal posterior, or you maximize the elbow. So here it's not the elbow, it's the negative elbow, so the opposite of the elbow. But so you have the two point of view. There's the projection point of view or the optimization centric point of view. And the optimization centric one is the one that we will be interested in today, because you can see this optimization centric point, this optimization point of view as minimizing a pack-based map, okay? And the last point, just like a reminder of the notations. So this is the distribution over which we minimize, okay? This is the prior, so the prior which is fixed. So here, this is the likelihood. So this is the log likelihood, negative log likelihood. So what we consider here is we say that the minimizer that we have is a balance between the fit to the prior and the fit to the data, which is the expected negative log likelihood. So if we minimize just this sum, this would be the best we could do would be just a Dirac in the at the maximum likelihood. If we just fit this one, we just get prior pi, and we try to balance the two quantities with an alpha here, which is present here because we tempered the posterior. So if we didn't temper the posterior, we would get a 1. So I think you are now familiar with this formulation. Now, what are the challenges of the lecture? So I wrote many questions. So basically, the only things we will do. So I will remind you, I will present you what are the conditions under which, so what does consistency concentration mean? So the precise notions I will use. Under which condition the posterior is consistent, the standard posterior, are consistent, and under which conditions can I have the consistency of the approximation? And then, so two small examples, and we will use pack-based inequality to show that the posterior concentrates, right? So a new divergence, that's a new Camellia. So the Rayleigh divergence, I will use that to study the concentration of the posterior. So basically, this will be used to modelize the distance between the distributions in the model. So between p theta and p theta prime, let's say, the distance between the two distributions will be quantified using this divergence. So I just a small reminder, so it is defined like that. And it is something when p and r are fixed, this is an increasing function of alpha, and when alpha goes to 1, it goes to the Camellia.
No, the exclusive.
Yeah, the exclusive. Yeah.
Same alpha as the temperature.
Yeah, exactly. Yeah. Sorry, you said?
It's the same alpha for the tempered.
Yeah, exactly. Yeah, exactly. So yeah, of course. So yes. So now I will introduce what is generally used in the frequentist Bayesian community to evaluate not the quality but the notion of convergence of the posterior. So we say that the posterior. So here's the temporal posterior, but this definition can be used for the posterior, the temporal posterior, the approximation, and so on. We say that the posterior distribution concentrates when this is true in probability. So what does that mean? It means that the posterior mass, the mass that the posterior places over neighborhoods around theta star, goes to 1. So basically, you consider you model, okay? So this is p theta star, p star, the truth, okay? And the point is that I'm telling you, consider a neighborhood around p star, okay? Of any size, you can choose the size. So this is the size of the neighborhood. what I'm saying is that if the posterior mass of this neighborhood goes to 1, as n goes to infinity, then my posterior concentrates, right? So whatever the size of the neighborhood. So if I choose a size of a neighborhood that is very, very, very small, if my posterior concentrates, I know that almost all the mass of my posterior will be inside this small neighborhood. So it's what I mean by saying that it concentrates, okay? It's also possible to define the rate at which it concentrates. So the rate of convergence of my posterior is the following. So it's almost the same definition. I say that the posterior concentrates at some rate if I have exactly the same definition, but I know which size of the neighborhood I should choose, okay? And if I'm saying a size of the neighborhood that is too small, for instance, smaller than the rate of convergence of my concentration, of my posterior, sorry, I will not be sure that all the posterior mass will be within this neighborhood. So actually, my posterior concentrate is if whatever the size of the neighborhood of the true distribution I choose, all the posterior mass is within this neighborhood. And the size of the neighborhood, the correct size of the neighborhood I'm allowed to consider is exactly defines the rate of convergence. Okay. So formally, it can be formulated like that. The posterior mass that is assigned to neighborhoods around the posterior is going to 1, whatever the size of the neighborhood you choose, but this is not allowed to depend on the sample size. But you can allow this to depend on the sample size, and the size of the neighborhood that you choose in the definition of the posterior concentration exactly defines the rate of convergence, okay? So for instance, if you consider, let's say that a posterior concentrates at a rate square root of n, 1 over square root of n, okay? It means that if here you choose a neighborhood of size 1 divided by the square root of n, then you can be sure that all the posterior mass will be within this ball. But if you choose a neighborhood of size 1 over n, you cannot say. I mean, basically, it will not contain all the mass will not be contained in the neighborhood of size 1 over n, okay? Otherwise, it would not define the correct rate of convergence. Is that okay for everyone? Great. And now, so this is not the notion of consistency we will use. No, basically, I'm just saying this because I will use results from a paper of Chérief-Abdellatif and Young, so fractional posteriors, that just was submitted in 2016 and published in 2019 in the Annals of Statistics. And actually, it's a notion that is very related, but which is everything is in expectation rather than in probability. This is quite convenient to work with because it's much easier to work with probability expectation rather than probability due to the fact that everything is linear. But it is very simple to understand this definition. Imagine that you have a pointwise estimator. Imagine, for instance, the maximum likelihood. How you wanna evaluate the quality, the consistency of the parameter is very simple. You consider the distribution associated with the maximum likelihood, the true one. You evaluate in Rayleigh divergence, for instance, the distance between the two distributions. And if this goes to 0, so either in expectation with high probability, whatever you want, then you can say that your parameter estimate is consistent, okay? If p theta hat goes to p theta star as n goes to infinity at rate Rn, you are saying that, okay, your estimator is consistent. In particular, for instance, for a simple model, you can even evaluate the distance directly between the parameters. Depends on the identifiability conditions that you have and so on. And when you consider distributions rather than single point estimates, it's exactly the same thing. Simply, you're considering the distance between p theta and p theta star, average over the posterior, right?
One question. So the identifiability for this would be important because if it's identifiable, then you know that this measure of discrepancy on the space of probability distributions induces one on the parameter space.
Yeah.
And that's only true if it's injected.
Yeah, exactly. So here we sample the data set. Given the data set, we define the posterior. So it depends on the data set. Okay, so we have two expectations: one with respect to the data set, one with respect to the posterior. You sample theta according to the posterior, and you take a look at the distance between p theta and p star. And if this goes to 0 in expectation at rate Rn, your posterior is consistent. How is it related to this notion of concentration? It's very simple. You can prove it in one line using Markov's inequality. So I remember that what I wanted to have was this. I wanted to show that this goes to 1 goes to 0, sorry, with high probability, improbability, sorry, to obtain the concentration. So let's consider the expectation with respect to the sample size. So here we use Markov. So the probability of this being larger than this is divided by the expectation divided by this. Okay. So this is Markov's inequality. This is straightforward. If we have the consistency, we have this smaller than Rn. So we have this smaller than Rn. So both this and this cancels. It gives you this. I just remind you that by definition, this Mn goes to 0 in the definition of the concentration. So basically, you have in expectation this quantity. In expectation, this quantity goes to 0 in expectation. So basically, the convergence in expectation implies the convergence in probability. So we have the convergence of this in probability, which by definition is the definition of the concentration. So if I assume that my posterior is consistent, which means that this goes to 0 at rate Rn, then I know that my posterior is concentrates at rate Rn. So this is I don't want to spend too much time on that, just to say that the standard notion of convergence is this one, the concentration. I will study the consistency, but it doesn't matter because it's simpler, so it's good for me. And if I have the consistency, I have the concentration too. That's great, okay? I can just focus on the consistency. Now, I will show you the results of concentration consistency for the temper posterior. So not the approximation, I'm still on the posterior distribution. So the condition is the following. So if I have such a condition, then my posterior is consistent and the rate defined by my condition. So this condition may seem a bit hard to understand, but it is very simple. It says that the probability mass assigned by the prior by around neighborhoods of the true distribution is non-negligible. Okay? So typically, you have your parameter, your model, okay? You have P star, which is the true distribution. What does that mean? It means that if all the mass put by the prior is here, it is all the mass that the prior assigned, all the prior assigned all its mass here, then you will not get the concentration. Okay. It says that at least an exponentially small fraction of the mass of pi needs to be around P star. Okay. So pi is the prior distribution is a probability distribution. So it assigns some mass somewhere in the model, okay, the parameter space. If all the mass is far away from P star, you will not get the concentration. But if it assigns at least an exponentially small amount of mass around P star, then you will be good, okay? So the only thing that it says is that, okay, this is called a prior mass condition. You require your prior distribution to put at least enough mass around small enough neighborhoods around your true distribution. Okay, so if I have if this whiteboard is the model and the true distribution is here and all the prior mass is here, you will not get the concentration. If at least a small amount of mass is here, then you will get the concentration. This is basically everything it says. Okay. So this is maybe a bit hard to formulate, but this is quite easy to understand. In the idea. So you see that for a radius of the neighborhood equal to Rn, you're allowed to put an exponentially small amount of mass around the neighborhood. So it is very, this assumption is very, very, very weak. Okay.
Very stupid question.
That
P theta star is the posterior, right? That true posterior that we are trying to.
P theta star? No, it's the truth. It's the data generating process.
Yeah, data generating process. Okay, so we need to have the prior mass kind of prior support around it. But I'm just understand is that if I have like completely misspecified likelihood,
Yeah.
that is my L theta that I've chosen is completely wrong, and I still satisfy this condition, will this still hold?
This is a very good question. I did not mention that, but basically, so we'll not go back to the slide, but I make for the moment the assumption.
All right, okay.
The model is well specified.
Okay.
I will explicitly mention a short result in the case where it is not.
Okay.
But here, I mean,
Here we assume that L theta. is
Yeah.
correctly.
yeah, exactly. And if it is not, to spoil you, if it is not, it's almost the same assumption, but on the best approximation in the.
Okay.
You mean, so if the true distribution is here, well, we expect to have some around amount of mass here, at least.
Okay.
You understand the idea?
Okay. Thanks.
No, thanks for the question. Okay, so the question is, one of the questions you can ask is, what about the consistency of approximate posteriors? Because here we prove the consistency of the temporal posterior. What about its variational approximation? And here we'll use fact-based inequality. So I will come back to I will still use the same setting, but try to make a parallel between this setting and the one using fact-based. So we consider IID random variables. So once again, I insist on the fact that the model is well specified for the moment, okay? So I have IID random variables. So it's as in fact-based, we had like pairs, but more or less the same thing. So we are given a model, which was previously we had like hypothesis, predictors, but more or less this will be the equivalent. We consider, so let's introduce a loss. So this can be like the way we will define the loss. So the loss here is the negative log likelihood, okay? Ratio, sorry. This is the log likelihood. This is a negative log likelihood. So this is a negative log likelihood ratio. And this is the loss that we will consider, which is not necessarily positive, okay? Or not negative. It may be negative, but this is the loss that we'll consider. Then we have an equivalent of the population risk, which is the KL between the truth and the parameters, the model, the distribution P theta we consider, and an empirical version of the population risk. So the expectation of this is this. So we are okay with that. This is why I say empirical risk, population risk, because the expectation of this population risk, empirical risk is the population one. But this is not really an empirical risk in the sense that it can be only computed using only the data, because it depends on the true parameter. Okay. So basically here, see, this is why I explicitly wrote the theta star, because it is empirical in the sense that it depends on the data, but it depends also on an unknown quantity. So it's not the complete equivalent. This is due to the fact that the thing we want to control here is not really generalization, but more concentration, okay? But you can draw kind of a parallel between both settings, right? And so I recall the previous fact-based bound when the loss is bounded, which is the following. So if the loss is bounded with high probability, uniformly over Q, I have the generalization gap that is upper bounded by the KL plus the confidence parameter here, okay? Plus, so this is basically the exponential moment. You remember the way the exponential moment of the generalization gap that we controlled using Hevding's lemma. But the particular point here is that we need to have the loss that is bounded by 1. And what does that mean to assume that the loss is bounded by 1? Is to say that the density here is lower bounded. So we need to have a lower bound on the density of the model, which is quite of a strong assumption, because, okay, if you have a finite support, then you can make such kind of assumption, but just imagine a simple distribution as a Gaussian. If you want to lower bound the Gaussian density, this is quite inconvenient, right? So typically, this kind of inequality is not really satisfying. And why is it important to control the loss? Because otherwise, we wouldn't be able to control this exponential moment. So to be completely fair, it's not a requirement to have a bounded loss, because even if the loss is not bounded, as soon as we are able to control this exponential moment, we're okay. So basically, if we replace the boundedness assumption by a sub-Gaussian assumption of the loss, that would be okay. What is important is to control this exponential moment. But I mean, even though we relax a bit the boundedness assumption by a sub-Gaussian assumption, still we will get problems here. So basically, the problem here is that with the distribution F that we define in the proof that we choose, so lambda times the generalization gap. Okay, this is very convenient to choose this one because we can get here the generalization gap explicitly, but to control its moment, we need to have strong assumptions, and we do not want such strong assumptions, right? So the problem here is this, because once again, so here what we did, I just applied this to our setting, okay? So I replaced the population risk by this and the empirical risk by this, okay? So the empirical risk is the so negative likelihood ratio. And the problem is, once again, unless I assume that the density is lower bounded, I cannot be able to control the exponential moment, so there is a problem here. And so the idea to obtain the result, so I will just first show you the result that we get instead of this one. So this one may hold under very strong assumption, and I can get actually without the boundedness assumption, this inequality, which is actually proved in the paper I mentioned just previously of Bhattacharya, Patian-Wang that was published in Another Statistics in 2019. So there are a few differences. The first one is that we don't have this exponential moment and we don't have any assumption. So this is a really, really cool result in the sense that we do not need any assumption, which was not the case here. Okay. But this is at some price. Here, we do not consider the KL, but the Rayleigh divergence. So is it better? Is it worse? In a way, it is worse because this is smaller than this. So basically, this inequality is less informative than this one. In practice, it's not really important because the difference between this and this in some models is not really huge. I mean, it's just a factor of alpha typically. So basically, when you're considering rates of convergence, it's not that important, but still you're losing a bit of information. And the second one is that the inequality is not sharp anymore in the sense that here you do not have a constant. You have a constant, but this is no longer equal to 1. This is equal to this quantity, which is a bit larger than 1. Okay, so you lose a bit. But what is very, very, very cool is that you do not have any assumption on the boundedness or anything, and you do not have any additional quantity. Okay, so this is very cool. This is a very strong result. And to show you how it is possible to get this, actually, it's almost the same proof as previously, but we will change a bit the function f that will be used in the proof. You know, the function f that was introduced in the change of measure inequality part. So basically, to tell you, so
Can I ask a small question?
yeah, of course.
So in the first inequality, it's quite natural to compare the KL with the R theta prime.
Yeah,
They're somehow on the same scale.
exactly.
It's natural to try to modify the R that you use when you're comparing to another.
So they are not on the same scale. So basically, it's exactly so we lose a bit, you know, in this is smaller than this, and this is a bit larger than just this. So basically, we lose a bit of information, but the 2 points is that in the end, what was interesting here was the generalization in statistical learning. Here, I mean, if we know that this is small, this is fine to us. So because we have the concentration, but in the end, if this is very small, I mean, or this is okay because this will be small as well. We'll just have like the rate of convergence is, instead of being Rn, it will be alpha times Rn. But I mean, that's pretty fair. And the other point is that, yeah. So in particular, you're right, because here, this is a central quantity that was used in statistical learning, the generalization gap, but this is not what is interesting to us. So we will be able, this is exactly the idea actually, to get rid of the exponential moment, we will introduce some bias here. This is the idea. So basically, so I just remember a mix of the first two ingredients. So we get this. So the change of measure inequality plus Markov inequality. And actually, the key point is the third one. We wanted to control the exponential moment. So actually, we choose this function, which is centered, okay? And the advantage of using this center quantity is that, so this is the same scale, exactly what you mentioned. But I mean, it's more a but than an and. We can control its exponential moment. We have to control its exponential moment, and we can control its exponential moment under a strong assumption, which is typically a boundedness assumption. If we use some kind of parallel, we would control this, but it would be the same. I mean, we would need a strong assumption on the moment, typically a boundedness assumption on the loss, which would be equivalent to a lower boundedness assumption on the model density, which would be very, very, very bad here. So the idea is to change the scale between the two quantities and to incorporate here some bias, so that indeed here what was an unbiased quantity would be a biased quantity now, but which exponential moment is equal to 0. This is basically the idea. So the idea is to cancel completely the exponential moment by introducing a bias. So here we will choose another quantity, which is this one. And if you take a look at the inequality, it's exactly this one. So it's n times 1 minus alpha times this minus n times alpha times this. Okay, I just multiply. As previously we multiplied this by lambda. Now we multiplied this difference by n times 1 minus alpha. And if we get this, so this quantity is not centered anymore. Okay, so we cannot use Hövdings as previously. Hövdings could be used because we had a central quantity. We end up with the generalization gap because we had a central quantity. This is not true anymore. But what is very practical is that the exponential of moment of this is equal to 0. I mean, the log exponential moment of this is equal to 0. And this is very convenient because this is true without any particular assumption. Actually, we just choose this function so that its exponential moment is equal to 0 without any assumption. And then, of course, we'll get, so it's not really a generalization gap, which is with both quantities at the same scale, but this is less important than this being equal to 0. So the proof is very simple. So I start with the second part. So if I consider the expectation of this, I write, so this is exactly the definition of the negative log likelihood ratio. N times this is equal to the sum of the log ratios. Then I use the independence assumption. So I write this as an expectation of a product is a product of an expectation. Okay. So here, so I just have not the whole data set, but just this. Then from this to this, I just wrote an expectation of a logarithm as just a quantity itself. So multiplied by alpha. So this is this I use the independence here. I just reformulated the probability. Then I just write this as an integral. So I multiply by p theta star. So p theta star divided by p theta star to the alpha is just p theta star to the 1 minus alpha. And I don't know if you remember the definition of the Rayleigh divergence, but it is exactly this. So this is exactly exponential of minus 1 minus alpha times the divergence between p theta and p theta star. And then I multiply it by, okay? So the proof of that is very straightforward. So this, without the log is equal to 1, then I can add the log and have 0. And then I'm done with the proof. So I introduce some bias. Once again, Fn, which was centered previously, is not centered anymore, but I do not have any exponential moment, which is what was important because I did not want to make any assumption on the exponential moment, on the density, sorry. Okay, so I have a very general result, which is the one I just gave you, without any assumption, with, okay, the two quantities not being at the same scale, but since that's, I mean, that's not the most important thing here, sorry, okay? Now to continue, so I just would like to give another result that is just a variant of this one. This one holds with high probability. I just want to give a result that holds in expectation, okay? So
A quick question.
yeah, sorry.
Last time you had the parameter lambda that you could pick to get a nice thing. So here, do we treat alpha in the same way as lambda before, or do we really, you know what I mean? Or is alpha?
Yeah, I understand what you mean. You can, I mean, the idea here is not to, ideally would be interested in alpha equal to 1. Okay? All these results hold with any alpha. You see, and if alpha is equal to 1, sorry, if alpha is fixed, this goes to 0. So even if alpha is a fixed quantity, this is fine. Okay. Previously, you had like the exponential moment that was like lambda over n. So you couldn't choose lambda as large as you wanted, okay? Because you had to do an explicit trade-off between lambda and n. Here, I mean, you can fix n and okay, that's fine. If you want to choose alpha dependent on n, you can do that. I mean, but you have to choose alpha, which is not too small, because if it is smaller than 1 over n, this would explode. And also, I mean, some people interested in the robustness properties try to find some tricky ways in practice to tune the alpha so that they can get robust properties. So, I mean, it's more an ad hoc, I mean, analysis that will get you, okay, maybe I'm interested in this property, so I'm interested in tempering this way the property, and if I choose such an alpha depending on n, will I still get consistency? But this is more an ad hoc procedure. I mean, it's not required to tune the alpha here to get consistency. So I was talking about the expectation, but it's the next slide. I'm sorry. What do you recognize here? So just a reminder about the definition. So the optimization-centric view of variational inference is the following. So here is just the opposite of the elbow. If you remind, just the opposite of the elbow. If I'm writing the negative log likelihood like that, so I did not do anything. This is the definition, minimizer of the opposite of the elbow. Just rewrite the likelihood. Now I add to the previous optimization program the sum of the log of the theta star. Why do I do this? It's free. I mean, it's a constant. This is constant. This is a constant. So basically, I can add to the minimization program any constant I want, right? This is what you did yesterday, Jeremiah. So basically, I can do this. But why do I do this? It's because here I can see the log likelihood ratio. And basically, I can the negative log likelihood ratio. And what is this negative? How can I write this negative log likelihood ratio? I wrote it like that. It's the empirical risk of the population risk. So basically, what do I recognize here? This. So actually, I can see the variational approximation of the temporal posterior exactly as the minimizer of this spike-based bound. So you can see a posterior, an approximation, a variational approximation as the minimizer of some spike-based bound. Okay. So this is equal to this up to this constant and up to this factor. Okay. And now I'm almost done with that. Just so this is the high probability. I mean, this is so. I mentioned 3 papers. So the first one, so I took the explicit formulation of the first one. Basically, the 3 papers I mentioned, the following, make exactly this. They have the same ideas, basically. So in particular, if this is valid for any distribution Q, if I apply in particular this inequality to the variational approximation, I have this. Why so? Because pi n tilde is exactly the minimizer of the right-hand side. So in particular, saying this applied to pi n tilde is exactly the same as in the infimum, because pi n tilde is the minimizer of the right-hand side. Okay. So in particular, I have this inequality. So I have this guarantee on the posterior, the approximation. So this is a bound with high probability. I also have a bounding expectation, which is the following. So this is what we call an oracle inequality. So we lose something here. Okay, obviously, this is not sharp in the sense that the constant is not equal to 1, but and also these are not the same distances, but still I have this inequality. So I actually the only difference is that I drop the dependence on the confidence parameter, which is not present anymore. And I just consider the result in expectation rather than with high probability. And here I take the expectation. The KL here is the expectation of the negative log likelihood rate. So I have this inequality. And now what can I say from this inequality? Something very simple. If you remind, actually, the notion of consistency I gave you in the beginning was that I could say that my variational approximation is consistent as soon as this quantity on the left-hand side goes to 0. the quantity in the left-hand side was exactly what I wanted to control in the beginning. So if I want to get the consistency of my variational approximation, it is sufficient to show that the right-hand side of the inequality is going to 0. Okay? So basically, as it is an infimum, it is sufficient to find a distribution Q such that this is small and this is small. It can be expressed like that. So the first result, if there exists a distribution Qn such that, so here, which is the first quantity, okay, is smaller than Rn. Here, the second quantity is smaller than n times Rn because it is the ratio divided by n. Then my variational approximation is consistent at this rate of convergence. So now you will tell me, it's still a bit theoretical, how can I interpret this? And actually, it's very, very simple to interpret this. I just remind you the case of the exact posterior. So this is the theorem for the variational approximation. This is the theorem for the exact approximation. Actually, these conditions are natural extensions of this prior mass condition. So this was the prior mass condition. You require your prior to put enough mass around some neighborhoods of your of the true distribution that is small enough. Actually, imagine that you're minimizing, so you're defining the variational approximation over the whole space. What would be your approximation? Your variational approximation would be equal to the posterior itself, right? Because you're like projecting over the whole space, and the projection over the whole space would be the posterior itself. So basically, if Q is equal to the whole set of probability distributions, in theory, this should be equivalent to this. And actually, there is a particular choice of Q, so which is the prior restricted to this ball, actually, which can be written exactly like that. So if you choose Qn, if you choose like Qn to be equal to the prior restricted to the ball, to this ball, actually, this inequality is always true. It is very easy to check, huh? To check, because by definition it belongs to the ball. And this is exactly equal to this. So basically, when the variational approximation is equal to the posterior, this condition is equal to this one. So this result is a natural extension of this one. And how can you interpret in the general case this condition? It says that you require the prior mass condition to be true. So we require your prior to put enough mass on small neighborhoods around your true distribution. And on top of that, you require your variational set to contain distributions that are concentrated enough around the truth. So it's as for the prior. You require here, you have only one condition, the prior mass condition, which is I require my prior to put enough mass around the truth. And this here, actually, you have two kinds of conditions. The first one, I require my prior to put enough mass around the truth. And another condition, which is I require my variational set to contain distributions that are concentrated enough around the truth. Okay? And if this is true, if you have good approximations of the posterior in your variational set, you have the guarantee that variational inference will pick up this one. Okay? So this is it. Actually, you have the consistency under a prior mass condition. So to go from the posterior to its approximation, you need on top of this prior mass condition, the requirement that your variational set contains good approximations of the posterior. You know, it's just that. If your variational set does not contain any good approximation, you wouldn't be able to do anything. But if it contains such good approximation, that's okay. This is everything it says. Okay? You have a question?
These are the exact like assumptions before starting variation inference anyway, right? That my family would contain the posterior.
Would contain not, because in general contain the posterior is never. But in general,
assume that would call.
Yeah, in general there. Yeah, in general there.
It's not necessarily containing the true posterior, right? It's more that you can actually get the objective on the right to go to 0.
Yeah.
So it's different. So this doesn't actually tell you anything about expressivity of the variational family. Here, the goodness of the variational family is purely defined in terms of the optimization problem itself. So if that thing, the objective can be made close to zero.
Yeah, exactly.
So that could be the case for a mean field family, even if you have multimodal distributions.
Yeah, in a way, it means that the variational family. Yeah,
Just because it doesn't relate necessarily to
Okay.
an explicivity of.
yeah, it's fine. Yeah. Thank you very much. Okay, so basically to cover the case mentioned, so the misspecified case. So this is what I can call an extended prime mass condition, which is the one on top. So you have the consistency under an extended prime mass condition, and assume now that the truth does not belong to the model. Actually, so I did not say explicitly the similar condition because it is quite ugly to write. I mean, it's an expectations of log ratios, but in practice, it's almost the same condition. It's just to say that, yeah, it's kind of a concentration condition on the approximation, and it's basically what we have is that this quantity. So of course, this will not go to zero because P star here will be far away from can be far away from any distribution in the model. So you understand that this condition will not be possible in general. If the truth is here, okay, and the model is here, the distance between this and this in Rayleigh divergence would be very far away. So this quantity cannot go to zero. It's not possible, not always possible, right? But what we say now is that this quantity can go to zero up to a constant, which is exactly the distance between the model and the truth. Okay, so it is measured in the ETL, not in the Rayleigh divergence, but it's exactly formulated as a trade-off between a bias and a variance term, right? Okay, so it's just like a small result to show that it can be extended to misspecified settings. Okay, great. And now I just would like to, because I told you that I'm focusing on the temper posterior case because it's simpler to analyze and the way the path from the tempered to the variational approximation of the tempered and the way from the posterior, exact posterior to its approximation are the same. So basically, I'm just giving you the conditions needed to get the concentration of the exact posterior. So this is the one prime mass condition that is needed to get the concentration of the temper posterior. If you want to study the exact posterior, you need to add one set of conditions, which are test conditions, which are the following. So I don't want to spend too much time on that as well. Just to say that the exact posterior distribution is consistent and concentrates around this plus this condition. And if you want to study the consistency of the variational approximation of the exact posterior, you just need to add the same kind of condition I did for the tempered as the other one, okay? And this analysis is conducted in this paper, Zhong and Xiaogao, which is one of the 3 papers that have been submitted and published at the same time, right? Okay, so just to say the path from the posterior, so tempered or not, to the approximation is more or less the same. So you have some subtlety for this case, but the idea is the same, okay?
So the tests you just need for the full posterior? Or...
Yeah, for the full posterior and for its approximation.
Okay, but not in the tempered case.
Not in the tempered case. That's why I did this one, because it's like much simpler. I don't want to do too much. But actually this paper showed that if you study the approximation of the exact posterior, you get exactly the same kind of conditions on top on the one you need for the tempered one. So now we are done for the second part. So I don't know if you want to make a break now.
Maybe 10 minutes.
Yeah, great. Yeah,
Going back to the misspecification.
yeah.
So if let's say I was conventional because the window and then approximate. So I wish here and actually
That's fine.
and to be bounded by like how if someone
What's the best choice?
It is also welcome.
Can you ask Mathematica to optimize and provide the paper for us?
finish a bit like but
Sorry, I'll leave
The process.
That there's always.
Solve that Kolmogorov equation. Of course.
Yeah, you can do the approximation.
Yeah.
In the theoretical side, it's not always I mean, this condition is not always the one you use in practice to obtain compute rate of convergence. In practice, because the condition, the case is a bit tricky. What I like doing, what I like in practice, that I split the problem into basically, distance between theta and p star is a problem. And p theta star, distance between p theta star and p star. So basically, I split the problem in.
Can we just?
Yeah, of course. Sorry. No worries.
I was talking to someone Baker's interested to join for dinner. So
Distance.
like he's free from like 5:50.
Because it's what I want to throw in the end.
I mean,
By this.
we could just meet
Theta star.
outside the great game.
Like the best approximation, so if the model is here, the best, just
You could do
plus my distance between, so it's a triangle.
right. Not even volume.
I don't know,
Where
generally, we applied the standard condition, so that. West 25.
algorithms that people don't really care about.
If I try to,
It works.
So I have time, I'd love to, it's been good fun, yeah.
try to. I mean, I think that these conditions are much simpler. Actually splitting the problem. Checking
Get like.
it's much simpler than.
I mean, I have
Directly.
my own money, so
So
if it's interesting, do you know what
Exactly
going to organize the next set?
Transport.
I'll wait for you.
Okay.
Yeah, no, that would be fantastic. Yeah, because maybe it's in Warwick as well, right?
We are planning to.
It'll be cheap to get.
Pretty cool.
It's not 100% decided, right? But this is.
Thanks for asking. No,
Does that fit with the ratio?
This one was in.
it does have a lot of funding that you need.
October and then the one in December, they all have been accepted the same year in the same journal.
Will only show up.
I can't guarantee 100%.
No, of course you can't. It's very kind of you to.
Yeah, it's nice.
Of course, your approximation, yeah, of course.
I'm not stop reading.
It's very relaxed there.
That's,
Not in a good.
we have a
No,
true
um,
approximation is,
I mean, obviously it's nice for me, I don't work.
always less.
So I got a lot of stuff just by talking to people.
I mean, it's interesting.
For myself.
It's when like.
It's a very high level. Never high probability of accepted from high density.
I was just the German. I don't know.
With the metropolis, so if you metropolize somehow the rate.
We're going to organize another one.
I don't actually know what.
Transport. I was thinking.
So essentially you approximate your probability with some.
If you want to come along, you should external attend.
That
means
then
basically
the step
pay for your
projection.
expensive.
It has to do with the approximation.
But you don't have to present anything. You
Like,
show up and
something different.
you're part of the group.
Hey,
But you can
I'll down and see what they.
like from
you know what you did?
different densities.
When? We haven't yet, but probably early May.
That's great because I have.
You have to burn money, right?
Yeah, I have funding and she's been
Yes.
for a year. Basically, May would be good.
Okay. We're aiming for that, yeah.
So it's like a
Yeah, okay. I'll,
factory from something else, will reject the trajectory.
Thank you very much.
It's a great way to get you back to the UK.
But the trajectory doesn't have
Lure you back on a.
the volume preserved.
yeah. And I don't know, I really like this group of
I
people.
guess it kind of
Not
is,
change it to hang out.
I guess to some extent,
We'll get some more.
for the PDMPs, it will be.
Straight lines.
But
Yeah.
so the reason I brought this up is because, right, like this can.
Yeah.
Doing some.
It would be nice,
Example I showed yesterday,
it would be nice if it worked.
it's not identifiable.
You still don't know?
The model isn't identifiable.
I think I showed. We haven't tried very systematically.
Okay,
Model.
so you have some.
Basically, the label switching, make sure that multiple solutions are all equally good.
You can always.
You could get that
suspect
the
nothing
zero
really, nothing that.
without actually recovering anything that looks any
My whole
stereo.
analysis.
So that's why I was like kind of intervening, because a lot of people, they think, as long as you
Look at this
variation
really balanced
family is like,
things.
there's no interplay between those two things.
Yeah,
Like the moment you specify the objective, it might be quite
It's like
it's quite distinct because you're operating in a different space, right? So you
Yeah, it's
optimize over measure. So that's why I felt like the need to bring that up.
Feel free to.
Yeah. No, it's pretty cool. I really like this. Do you have your slides somewhere? Because I've been meaning to read these 3 papers anyways, and I have vague cursory knowledge of it,
I can check then you get,
especially Pierre's.
get a different functional equation that looks a little bit like what you
Pronounce his name, but
Yes. And I couldn't basically make it strong as well.
but no, you say with such confidence. No, but it would be great to go over these. I think with Masha as well. I can be prepared for that. So I'd love to forward that.
You were saying this scaling, people show to go and so on. Analysis.
I read it once in the beginning.
Yeah, because
They changed their versions many times. I mean, with very consequent. I mean, the last version is very good, but I'm not sure I read the last version to be
Okay.
honest.
I order.
But
That's fine. I mean, if there's 3 papers basically doing the same thing, it's okay. That's actually good, right? You can
Yeah.
pick which one suits.
the thing is,
I definitely don't like testing conditions, so if I can
Yeah.
avoid those, I never know what on earth there's about, to be honest.
actually, yes,
A random.
you know the paper I didn't.
Yeah.
Actually, some guys.
Yeah, you have testing conditions in that as well, don't
I
you?
don't.
You don't,
because
okay.
I consider it tempered, but some guys did it after me,
Ah,
and
okay.
it was like just did computation. Well, okay, it's obvious, it's satisfied. I was like, okay. Useless.
Oh, no.
So yeah, it seems like it's. There are not. I mean, it's a bit tricky in I think in Bayesian non-parametrics when you have
Yes.
some kind of situation.
I'm tired in general.
Oh,
It's my state of being exactly.
Piece of messages of
Exactly.
Densities of, right?
yeah.
We know how much it makes me pay.
That's actually there's an infinite extension for it.
The baby crying in the night.
Really use the KL inference.
Yeah.
Works a lot to get.
It might give me.
I used to already done it, so.
Find a job, basically.
I think, people have tried to do more
Maybe there's a few.
differences in there when for no good reason, actually.
They skip
In the non-parametric case, you might actually do that.
Oh, wow.
Access to other conditions that are really
Time.
unreasonable.
If you fell back
Lately.
No, because you can't compute it. But so you would have to do and like an IPN.
I think I've seen some people, but not doing Badr. Just interesting. But not necessarily this kind of, optimizations.
Yeah.
The optimization centric point of view, it's like that.
There's a paper in Europe this year from the student. That's now.
If
Basically
didn't
use
have-
Wasserstein
You get you just.
as a regularizer because he works in it.
Okay.
And then you can't use
But-
KL.
So,
So it's, what's it called?
so I
I
think
think
that.
it's just called generalized variation.
Does it suggest that if you,
He can actually improve. So he extended the sort of.
unadjusted HMC versus unadjusted.
This is because it still kind of works, like you can still write everything as an optimization, which isn't necessarily obvious. And so. Yeah.
Probably not. It's just a complete line.
That as a starting point.
It seems like not
Basically.
really start maybe reading it in this one way.
Sorry, oh, sorry.
Oh, yeah.
Show up anywhere else in like just convention.
Okay, we're back.
Great. So the last part. So this is just like simple applications. So 2 applications. So the particular case of mixture models and the particular case of sparse deep neural network, which are case I've worked on. So basically, the main messages of this section are the following. Very simple. The first one is that if you want to estimate a mixture, a model with some rate of convergence, estimating its mixture is a mixture of k components, it's k times harder. This is the main message, okay? So this is the first message. The second one is imagine that you're in a non-parametric regression problem setting, okay? And you want to estimate a smooth regression function. If you want to do so, it is possible to use sparse deep neural nets. And you can do this with the optimal rate of convergence. So we'll explain what I mean by minimax optimal, but it's optimal. And the third one is that there is no price to pay to use variational inference. So once again, the rate of convergence that we get by studying whenever we use standard Bayesian inference or if we use like variational inference is the same, actually. We do not pay anything to use variational inference instead of standard Bayesian inference, right? So first, the case of mixture models. So imagine that we have densities, but once again, this is not really important. So Wj are the weight here, P theta are the components. So here it is the simplex, right? So all these components are positive and non-negative and sum to 1, okay? So this is a mixture model, and each model can be written like with P theta. So the log likelihood is the following. So it's not just the log of the likelihood, of course, the mixture of the densities. And so of course you will have like tractability problems with this. So we adopt a Bayesian approach. So we we choose this prior. So we put independently a prior over the weights, a prior over each component. So with the independence, so it's kind of a mean field prior. And we choose a mean field variational family, which is that we put a distribution over the prior, a distribution over each parameter component, and choose like an independent posterior, approximate posterior like that. Okay? So this is standard, you know what is, I think that the mean field family is quite suited to mixture models. So this is just the optimization program. So I'm sorry, so this is here, okay, this is the KM. So the optimization program is the following. It's a very simple optimization program. So basically, if you want to solve it quite efficiently, you can do so. So it has been presented in the masterclass of the KEV algorithm, so coordinate descent variational inference. So we can use like kind of latent variable and to solve it quite efficiently by optimizing in QW, the order being fixed, and then alternate. So this is something that has been presented. I will not spend too much time on that, but just to say how we can optimize this quite easily. And the result that we have is, so for convenience, I will choose, actually the main result is that we can split the problem in two. So how difficult is it to estimate a single component? And how difficult is it to estimate the weight, the mixture weight? Okay, so I will fix the prior I choose over the mixture weight, okay, which is the following. So it's a Dirichlet distribution, so which is quite standard. I will not spend too much time on that because it's not, I don't think it's what is interesting here. But basically what I have is that if I choose this prior over the weights, I have the following result. So what basically it says that as soon as I can estimate one single component, so these are the conditions for one component, okay? So I say, okay, they have to be true for each component, but basically, if the prior mass, the extended prior mass condition is satisfied for a single component with rate Rn, then I know that the rate of convergence, I know that my posterior is consistent, and the rate of convergence is equal to k times the rate of convergence for a single component plus k over n, okay? So you see two terms here. So this term comes from estimating a single component, okay? And the other term, k over n, comes from, so k times this because it's k times harder, plus k over n comes from estimating the weights, okay? So you have two components, y for the weight estimation and y for a single component estimation. So basically, this is a very fast rate. K over n is something that is very fast. And in general, this will be no faster than 1 over n to a log term, okay? So basically what you have in the end is that if you assume that you can estimate a single component at rate Rn, then the rate of the consistency of the approximation will be possible at rate k times Rn. So k here is the rate, is the number of components, and Rn is the rate of consistency of a single component. So this is basically the main result of the paper, right? So typically, I will just try to let you like a few minutes to try to compute the rate for Gaussian mixtures. So basically, we have like IID random variables from a mixture of Gaussians. So their variance is 1. So the true weights are unknown, the true components are unknown. So for fun, we will use like Cauchy prior distributions. So not Gaussian one, but that's not really important. And we will use like a Gaussian family. So we use the mean field family, but each component you will place over each component a Gaussian variational approximation, right? So what you want to do is to be able to compute the rate of convergence for a single component. So you have a Gaussian family, a Gaussian model, okay, and you want to compute the rate of convergence for estimating a single Gaussian. So you want to find a distribution Qn, such that this is smaller than Rn, this is smaller than n times Rn. And I'm just helping you. So just in the end, what you want to find here is the rate of convergence, the distribution such that this and this is true. And I just like 2 hints. So this is equal to this. In the case of Gaussian, this is like pretty basic. And the distance between a Gaussian and the Cauchy prior distribution is bounded by this. So now the only thing that you have to do, so it's very short, I will maybe give you 5 minutes, is to find a distribution Q such that, and a rate of convergence Rn such that this and this is smaller than this and this. That okay? So here, by checking this condition, you just check that the extended Poisson mass condition is satisfied for a single element, single component, sorry. And finding this Rn and finding a Qn, so finding a Qn means finding an Mn and a sigma n, is exactly what you have to do. So in practice, when you want to compute rates of convergence, you have to check whether it is possible to find a Qn and a Rn such that this and this is true.
So here the x1 up to xn are from p theta star, which is a single component.
Sorry?
The p theta star is also a single component, or?
Yeah, just now imagine that you, so we consider a Gaussian model, a Gaussian mixture, but to check that the posterior for the mixture is consistent, you just have to check the consistency for one component and multiply the rate of convergence by k, sorry. So now let's forget that you have a mixture. Just imagine that you have one model, which is this model. Okay. So you consider this variational approximation for each model, given this Fourier distribution. And you just want to check this kind of inequality.
Are we assuming we know Q?
In the second box,
Yes.
Yeah, okay. Okay, so are we writing it on? Oh, sorry. This. Yeah. So this thing, let's see, one. Okay, and this is. And I mean, once you look at this thing. And actually, that's just. We'll get exactly. So basically means first. And now all you want to do is. You get the opposite way. So if you wait. So you're saying it goes to zero. If you see, so if you write this is a function of n, that goes to zero. Okay, this goes to zero. So we want r n.
You have to have that n times Rn go to allowed to diverge.
We're happy with. I'm not sure in that precisely. Choose like.
Yeah, the log is always good.
Times Rn should diverge.
For instance,
Okay.
in long and bell, I think it's.
Okay.
So in general, it's a spoiler. It's some.
Yeah.
Logarithmic term is one of the square root of n.
So how you can.
In general, if you're in a good situation, it's typically what you call. I mean, one of the n because it's like the clearly it would be one of the n. So typically, what you need to do. So yeah, in the end, you expect to have something like one of the n. So you need to tune your sigma.
So like I'm thinking something, if you take the mean to be theta star.
That's exactly what you have to do.
Yeah, so then it's just choosing this, right? This Rn, which is.
Yes.
Which is the sigma.
Yeah, so yeah, I don't know if it's exactly because just like you actually once you've done this, theta star, yeah, you exactly the idea is to say, okay, variance small enough, so something like one over n, let's say, and then you check that Rn, you can have the two quantities which are of order one over n. So basically, just put Rn equal to the max quantity.
Okay, so this is the.
The thing is, for example, here you have two m's. M is theta star. So this can't be uniform. It has to be theta star.
But no, not for all. Yeah, I'm sorry.
Oh, okay.
Yeah, just like sorry, just like here, it's not true for all theta star. It's just like theta star is fixed here. Okay, it's not uniform in theta, right? You can take it as granted.
I see. So this is actually just a constant term.
Yeah,
So this doesn't matter.
exactly.
Oh, okay. Yeah,
Ah, that's the.
Yeah.
Okay, so that explains. Besides, that's Q1, right? We not choose this normal. Yes, yeah, yes, yeah. So we just have to fix signal.
Maybe 2 minutes.
So you're taking basically like sigma square and equals to.
Yeah.
Yeah.
So you get sigma and it's like one over n, which sounds about right. Yeah, because basically you can ignore this term, right? 'Cause it's
Yeah,
log,
exactly.
and then this is just 2 times r. That's the same.
Yeah, basically, if you choose like random.
Sigma square.
Well, actually, I think well, it depends how you parameterize it. So mine was sigma n squared, so then Rn is 1 over n squared.
So basically what I did in what you can do in this requirement, but you can choose it to be over the one. In which case you directly have one.
No, sorry, I'm just trying
Then
to.
you put Rn to be over Rn as well.
So we.
It depends on how you, because you're free, you're free to choose M, sigma n, and Rn.
Mhm.
So basically, in the end, you can be happy. You just have, in theory, you will have log terms, which are like, some people care about them. Some people care about them, but yeah. So yes, so let's dive into the computations. So basically, you have this. So the question is it possible to find a rate of convergence Rn and the distribution Qn? So that is, I mean, Mn and the variance sigma n squared, so that the first inequality holds and the second inequality holds. Okay. So basically, this is just the expectation of that. What is the expectation of that? It's quite easy to show that this is equal to, okay? So you just split this thing in two and you exactly get this. So basically, you see that if you want this to be small, the best thing to do is to choose sigma Mn, to be equal to theta star. Otherwise, it will be very difficult to get something that is small. So you first take Mn to be equal to sigma star so that this cancels. And basically, the idea is to choose an approximation Qn, which is really centered around the truth. So if the truth is theta star, so you choose a Gaussian, which is centered at theta star, and which is very centered around this one. So let's take, for instance, 1 over n, okay? So if you choose this to be equal to theta star and sigma squared to be equal to 1 over n, you can check that the rate of convergence will be typically 1 over n, which is in the end more or less what you want to have. A good rate of convergence in K-half typically would be 1 over n, okay? So if you choose this, which means that the approximate posterior will be very centered, concentrated around the truth theta star. This term is equal to 0. This term is equal to 1 over 2 times n. And the other quantity, so you just sigma n squared is equal to 1 over n, so you get this, okay? So this is a logarithmic term, right? Log n. This term is a constant, right? And this other term is equal to the square root of 2 over n. So basically, this is just a logarithmic term, which can be, so basically a logarithmic term is upper bounded by, so it's not a constant, but it's a logarithmic term. And basically, if you choose Rn to be the max between this term and this term, okay, because you want Rn to be an upper bound on this and on this divided by n. So basically, you choose Rn to be the max of this and this divided by n, and we exactly get what you want, okay? So once again, you choose, ideally, this is what you want to have. So you choose the posterior so that it is centered around the star, the truth, with tight variance, 1 over n. So you compute the first quantity, you compute the second quantity, and you choose Rn to be equal to the maximum between the first quantity and the second quantity divided by n. And basically, so the first is equal to 1 over n, the second is bounded by this, okay? So this divided by n is larger than this, so you put Rn to be equal to this second quantity, and you get this. So something which is log n over n. So the final rate of convergence that you get is 1 over n up to a logarithmic. Okay, and the final rate of consistency of convergence of your, yes, Philippe?
Oh, because you put into nothing. Go on.
Okay.
Sorry.
No worries. And so the final rate of convergence of your posterior for the mixture model is k times log n divided by n. Because I'm sorry, just one times, because this is about log n over n, right? So this is the final rate of convergence that you get, k times log n over n. So basically, the only thing that you have to keep in mind when you're considering mixtures is that the problem is just considering a single component. You solve the problem for a single component and you're done, right? So this is just basic computation. So we'll see after that the case of sparse deep neural nets. So we'll not do the computations because it's very cumbersome, but basically the idea is once again the same. I mean, it's just much more complicated to dive into the derivations, but the idea is more or less always the same. You have an idea of what you would like to have. You try to find a good variational approximation, which is centered enough, and then you tune during the computation. Okay. So this is all for the measures, and regarding the sparse deep neural net. So basically, so you're in a non-parametric regression framework. So you have a random design, okay, uniform random design. So you have an unknown regression function f star with a dot noise. Do not make any particular f star for the moment, and you want to approximate f star by deep neural nets. Okay. So here, typically, the depth of the network is 1, 2, 3. The width of the network is 1, 2, 3, 4. So so what we will do is that we will just like switch off many connections, and the number of active connections is what we call the sparsity of the network, okay? And so here, capital S, so capital L is the depth, 3, capital D is the depth, is the width, sorry, so 4. So this assumption that it is smaller than the size of the feature space, it is much more for convenience. It's not something that is important at all. So the total number of connections is capital T, S, capital S is the sparsity level of the network. So here the parameter space is composed of weights. So all the weights, the connections between the different neurons in the network with the biases. And finally, you can, so here, if you do not row the activation function, then you can define the neural network predictor, right? So if you're familiar with neural nets, it's just like a standard setting. And typically, so the spike and slide, the prior that we choose is the one that has been used by Veronica Rakova and Paulson in the Neurops paper 2018. So basically, it's a two-stage prior distribution. So first, so the network is sparse. So you only have a capital S number of connections that are active. So the first thing that you do is that you select uniformly at random a set of active connections, right? So uniformly at random of a data set, you select capital S connections. And then for each connection, you have two situations. Either the connection is non-active, in which case the weight is put to 0, right? With probability 1, because the connection is non-active. And the connection is active, in which case, under the prior distribution, the corresponding weight follows a Gaussian distribution, a standard Gaussian distribution, okay? So here, you select a number capital S of active connection, a set of capital S active connection, assume that this connection is non-active. So in this case, the weight associated under the prior will be set to 0, with probability 1, or this connection is active, in which case the weight under the prior distribution will follow a standard Gaussian distribution, right? So this is the way this prior is distributed. And, sorry, so what we will do here is tempered Bayesian inference. So we use Bayes rule that we temper using an alpha parameter. So this is the way we define the temper posterior distribution. So of course, given that we have a sparse deep neural network, this is intractable. So we will approximate it in practice using variational inference. So the question, how do we choose the variational family? So the answer is pretty simple. Actually, we choose exactly the same kind of family as the prior, but with two small differences. The first one is that the way we select the active connections is no longer uniform at random, okay? So the way you select your set of active connections is a hyperparameter of the variational family. And then either the connection is non-active, in which case the weight is set to 0 with probability 1, or otherwise the weight is set to follow, it follows a Gaussian distribution, but this mean and variance are now hyperparameters of the variational family, right? So once again, it's a two-stage distributions that have more or less the same form as the prior distribution, right? Is there a question regarding this process? So now basically what we have, so we define what we can call the generalization error. So it's exactly what I said from the beginning. This is a regression function. I do not make any particular assumption on the regression function, right? We approximate it using neural nets. So here theta follows the variational approximation of temper posterior. So the generalization error is measured in expectation and in expectation with respect to the sample of according to the approximation and with respect to the data set. So typically this is the squared distance between a neural net sample from the approximation and the true regression function. And the result that we have is the following. So basically, we know that the generalization error of the variational approximation that we did achieves some kind of trade-off, kind of balance between, this is an approximation error. So how expressive is our set of neural nets, right? So this is small as soon as it is true that the true regression function can be approximated by neural nets, right? Which is, we know it is known that neural nets are very expressive. So this is very likely to be small. And there is another quantity, which is what is the estimation error? So the rate of convergence because this is typically a misspecified setting, right? So this is the rate of convergence that I would have if my setting was well specified. And actually, this statistical error is linear in the depth of the network, linear in the sparsity of the network, and logarithmic in the width of the network. So this is depth, sparsity, D is the width, and N is the sample size, the number of data. And just a small word on this result. So this is a trade-off between which can be referred to as the bias, the approximation error, and the statistical error, which is here kind of the variance. And what is interesting here is that actually both quantities have opposite results and opposite dependence on the architecture of the network. Here we see that this variance term is linear in the depth, but is logarithmic in the width. What it means is that if you add more layers, these terms will grow linearly. But if you add more neurons per layer, then this rate will not be affected at all, almost not, only logarithmically. But the behavior regarding the depth and the width is the opposite here. It is not that you can gain really a lot, an exponential expressivity by adding a few numbers of layers, which is not the case when you add neurons in one layer. So basically, here, what it says is that your generalization error will be very good, the variance term will be very good if you add neurons in width, okay? And here, these terms say, okay, you want a better result, add layers, okay? So this is kind of a balance between them. Here, it's better to add depth rather than width. Here, it's better to add width rather than depth, okay? Yeah, Tom?
So you said that when you add more depth, expressivity increases exponentially. So do you have
compared to the increasing the width, yeah.
So do you have any results for that?
So there are these results. So not here, but basically the
result from Yoshua Bengio's work.
Sorry?
Yoshua Bengio's work, there's some result from.
Yeah, definitely. There are some results regarding that. So implicitly, I use this kind of results in the following result. Actually, if you know something about this function, for instance, it is Hölder-Smooth. And so in this case, you know what is the best rate of convergence you could have. And the following result, we show that we can tune the architecture so that the optimal rate is a shift, right? And the optimal rate is like a trade-off. The optimal architecture balances the two terms. And this is a shift by a trade-off between this and this. And explicitly, I use this kind of results, but I do not know. I don't have in my head some references regarding that. But such results, yeah, they do it. So the following results. So yeah, just some remarks first. So the main idea of the proof always the same. So it's pack-based theory plus the extended prime mass condition. So here is kind of a prime mass condition. So if you check this kind of condition, so this is more painful than the previous derivation that we did, but in the end is the same thing, exactly the same thing. Okay. And what is interesting as well is that this rate of convergence, so this variance term LS, this is exactly what people get when they're doing simple empirical risk minimization. So the object that they study is very different. Here it's like variational Bayesian inference. In their case, it's just like empirical risk minimization. The technical tools that are used here, pack-based, and in their case, like tools like local covering entropies are very different. But in the end, we get exactly the same result, which is that the variance term is equal to constant, of course. Okay. So basically, just to say that this is disagree with the other result that exists in the literature, but even with different estimators. And finally, so this is more of a theoretical result, but let's assume that the function is Hölder-Smooth. In this case, we know that it is possible to estimate this Hölder-Smooth function at this optimal rate. Okay. And what we show here actually is that if you tune the depth, the width, and the sparsity of the network, then the variational approximation of the posterior concentrates at the optimal rate with a square logarithmic factor that actually this square logarithmic factor is always present, even with when considering empirical risk minimization. So this does not come from considering Bayesian inference or variational Bayesian inference, but it's just to say that this. So I talked about a trade-off between the bias and the variance with the choice of the width and the depth of the network. Actually, in practice, if you have some assumptions on the regression function and you want to achieve the optimal rate, it is possible to achieve so by choosing wisely the architecture of the network. It is indeed a trade-off between the right width you should choose and the right depth you should choose, right? And the sparsity as well, because here you have some sparsity. So this is mainly, this is what exactly I presented as being concentration with some rate of convergence. convergence in probability. And just a final slide, just to say that actually this is very limited, this work, because in practice it is quite complicated to compute this variational approximation, even if it is like, I mean, to compute it in practice at large scale is quite complicated. So there has been a work by Sung and Cheng, so we are people in the US that actually relaxed a bit the choice of the variational family by imposing a mean field approximation. Okay, so they still impose a sparsity, but they say that for each component, they say, okay, with probability, they say S is the sparsity level, with probability S over the number of connections, the probability is active, otherwise it is non-active. So the main difference is that they do not fix the support of the active connections, but in expectation, they can select a number of connections which is equal to the sparsity, but they really impose this independence between all the connections in the network, which is not true here, because the sparsity is fixed. So the number of active connections is fixed. So it's not possible to have some independence, because if you have like S minus one active connections, you know that there will be one remaining active connection. So basically, there is some independence. So they impose there is some dependence, sorry. So they impose the independence in the network with the sparsity being achieved in expectation. Using this and some relaxations, they compute it efficiently in practice. So they get the same kind of concentration results. I mean, exactly the same kind of results. In theory, in practice, it works quite well, but yet it's not the kind of things that are used in practice, because in the literature, mainly people do not really choose sparse networks, or at least they can use pruning or some kind of things, but this is not basically what they do. So yet this is still most theoretical works, and there's still a lot of work to be done on. Thank you for listening.
It can be connected to dropout, I guess.
Yes, but the difference is that here the sparsity level is something that is really small. Basically, it has something that must go to 0. So basically, the dropout level that are used in general is not something that is really negligible. It's something like 10%, something like that, right? So this is not exactly